Hi, Carlo. How are you?
Hi, Professor. How are you?
Hi, Carlo. How are you?
I'm fine. I'm fine. Yeah,
Good.
We can hear you. It's okay.
That's good. So, when do you start?
We will start with the welcome to the workshop at the 20 past 11.
Okay.
And your speech is scheduled at 10 to 12. Yeah, I will send you the agenda in the chat.
Oh, that's good. No worry. So you have got how many people you are expecting?
Well, the registered attendees are 750, but
750?
yeah, registered.
Wow,
Yeah.
that's a big number.
Yeah.
That's a huge
we are
number.
very proud of our work. I don't know how many people are connected now, are around 20, but
yeah.
still,
No, that will. So even if you get half, so it will be almost 350. So
yeah. It depends on the different times around the world. We have several registered attendees in USA, so probably in the afternoon will be better. It depends.
Yeah. No, that's good. Okay.
Yeah.
Okay. Anyway, I'll be online, so anytime is fine. Okay.
Okay. Thanks.
Okay. Yeah.
Ladies and gentlemen, it's my very great privilege to welcome you all to the second edition of IEEE International Workshop on Wearable Sensors and Devices, Artificial Intelligence and Wearable Markets. My name is Carlo Massaroni, and I'm one of the general chairs and the local chair of the workshop. Last year, when me and the other two general chairs started organizing the second edition of the workshop, I enthusiastically accepted the challenge. I was very optimistic while considering the organization of IEEE WSAIM 2021, not just because of the success of the first edition of the workshop, but because of the topics we have imagined inside the new edition of this workshop. In IEEE WSAIM, we will explore different aspects of the wearable biomedical sensors, from sensors design and development to the artificial intelligence algorithm and machine learning for medical application, to the market of wearable sensors for healthcare, occupational settings, and sport monitoring. Due to the COVID-19 restrictions, all the organizers devoted a significant effort to organize WSAIM 2021 live and to tackling the gap between a full live conference and a full live conference online. As for the previous edition, IEEE WSAIM 2021 is broadcasted online via Zoom platform. All the plenary speakers will take their session live. We hope that this solution will allow all the participants to interact with each other, to interact with the speakers and the chairs, and to enjoy this live workshop. Part of my duty is to provide you a short introduction to give you at least thumbnail sketches to what this workshop is and to what we are going to do in these 2 days. IEEE WSAIM 2021 is dedicated to provide the latest research findings, ideas, and applications in the area of wearable sensors and systems, artificial intelligence and machine learning, and to understand how the wearables markets are evolving. This workshop is intending to provide a forum for research scientists, engineers, and practitioners. And we will provide you all the best tools to interact with our top-level speakers during the whole conference. From the very first moments, we wanted to organize a workshop completely free. It was a strategic choice to allow anyone to access the contents of this workshop and to interact with scientists and leaders from all around the world without any economic and social restrictions. Here are some statistics to better understand the workshop. Today, we have 722 registered attendees at the workshop, 550 more with respect to the first edition of the workshop, with registration come from all around the world. As you can see at the IEEE WSAIM, 66 countries are represented and shortly depicted in the color of the board map, 4 more than in the first edition. The general chairs and all the organizing committee members are very proud of this result. And the merit is mainly due to our 16 speakers that we will get to know better in a little while. Looking at the provenance and affiliations, we can see that the majority of attendees are from Europe, North America, India, and Asia. But South and Central America, Africa, Middle East, Oceania are also well represented. And we are extremely happy to see participants from academy, companies, and also from other organizations and governments. Thanks everybody to join our workshop. Now, let's see how the workshop is organized. This year, WSAIM is organizing 4 main tracks. In the first day, today, we will explore the point of view of our speaker about the impact of wearable sensing devices for the physiological and physical monitoring, and design and challenges in the field of wearable sensor and devices. Tomorrow, the 2 tracks will be devoted to present the current and future trends of wearable sensors markets with speakers from companies and an overview of machine learning and artificial intelligence and how machine learning is evolving for the analysis and decision analytics. Let's get to know the speaker quickly. In the first track, Professor Tamura, Leonard, Tunchera, and Professor Camamilla will provide us an overview of current trend of wearable sensors and body sensor networks for medical and sport application, as well as how to tackle with energy sources in harsh environments. In the second track, Professor Mukhopadhyay, Kim, Lo, and Occhipinti will allow us to better understand how to design a wearable sensor and the open challenges in the field of health and well-being. In their talks, we will see biosensors, new materials for capturing physiological quantities, microelectronics integration for sensing application, new enabling technologies, even energy harvesting to push forward the current application of both wearable and implantable devices. In the third track, the track dedicated to companies, Dr. Pau from ST Microelectronics, Seppa from Revenue Research, Nicolaudis from SAP, and Vidyanathan from Movella, Exit Sense, will talk about their experiences in the field of wearable sensors in different scenarios and the current and future trends with insights on how turning academic research to medical device businesses. Lastly, track 4 is devoted to machine learning and artificial intelligence. Dr. Carini, Professors Mandich, Inan, and Lee will give us an overview of the interoperability of data collected from wearables, advances of computational methods and techniques, even based on machine learning and artificial intelligence in the field of physiological monitoring and human performance, and also personalized rehabilitation. In this slide, a short overview of the agenda of today, the first day of the workshop. After the welcome talks from our technical sponsors, the first track will start at 10 to 11, while the second track at 4:30, with the last page scheduled at 6:10. The agenda of the second day is similar, but at the end of the day, we will be very happy to give you information about certificates of attendance, statistics of the workshop, and anticipation of the third edition of the event. During the organization of the workshop, we have worked with IEEE Young Professional Italy Affinity Group, and tomorrow, 14 December in the morning, IEEE WSAIM will host the IEEE WSAIM Young Professional Pitch Competition Award, dedicated to master students and young professionals. The competitors have prepared a 5-minute videos aimed at showing their research activity using slide, picture, photos, graphics, lab demo, to describe in a convincing and attractive way their research result and field application. The IEEE WSAIM participants will be able to vote their favorite video using a special application, Mentimeter, on their smartphone or other devices during the participation to this special event. All competitors will receive a participation certificate. The best video will be awarded with a customized certificate, and the winner will receive a €500 prize. The award recipient will be selected by the award committee from Federica Battisti, Vincenzo Randazzo, Davide Comite, Elisabetta Muisello, who I want to thank for organizing this wonderful event. Then I really want to thank our great technical sponsors. At the end of my welcome speech, each sponsor representative will greet you with a little speech. And I want to end by thanking all the colleagues involved in the organization of the workshop. I want to thank the two general chairs, Professor Bonato and Professor Varadarajan. It has been great to work with you during the last months, and it has been great to have someone so expert and brilliant in my corner to help me to organize in the best way possible this workshop. On behalf of all the general chairs, a special thanks to the 3 technical program chairs, Majorana, Gravina, and Scana, the publication chairs, Savaglio and Guerrieri, the publicity chair, Silvatti, and the finance chair, Bergamini. Finally, I'm so grateful to all the organizing committee members. Their work has been important to improve the organization of the event and its promotion. You make everything not only possible, but also very spectacular. Thank you very much, guys. Well, IEEE WSAIM 2021 is officially started. Please enjoy the workshop. And it's now time to leave the floor to the technical sponsor representative. And as first, it's my great privilege to introduce Dr. Palmer, Chair of the Technical Committee on Wearable Biomedical Sensors and Systems in IEEE Engineering and Medicine and Biology Society. Thanks for your presence here, Dr. Palmer, and the floor is yours.
Thank you very much, Carlo. I'd also like to thank the other chairs Vijay and Paolo for your hard work and putting together another wonderful WSAIM workshop for everyone. You know, IEEE and EMBS are dedicated to impactful, diverse, and inclusive workshops and abilities to share and learn information across the world. And this is a wonderful example of that. How many workshops can you attend for free and still get prize money out of? It's amazing, while learning about the best research technology that are available worldwide. It's truly an amazing workshop, and we're very pleased to be part of it and to be a technical sponsor. With that said, this is also one of the fields where personally, as the chair of the WBSS, Wearable Biomedical Sensors and Systems Technology community, I'm very interested in seeing different communities come together, seeing academia, seeing industry, seeing the clinical elements as well as different types of research across the board, pull ideas and make them a reality. Now, we all hear a lot about artificial intelligence and machine learning and the promise that has for the future, and it is large. But this is one of the unique times where you can actually live that future now. The fields that you'll be hearing about, whether it's physiological and physical monitoring, wearable sensors that you're probably already wearing right now. The machine learning is actually in person. You can see its impact. You can feel it. And sometimes it may even save your life right now. We'll even be able to take a little bit of a look beyond what's here today and look into that future with the future trends in the wearables market, as well as how that will impact you in the clinical or on the sports field. So it's my pleasure to just start that look right now, and also think about the wonderful ability for you to be able to pitch your own ideas, especially if you're a young professional, and against the top ideas from others from around the world for a competition that will be fun. And also, for one, you'll get a prize as well. I'm so excited to see how this will turn out, not only the great talks, but the competition over the next day, and see your wonderful ideas. Thank you again, Carlo, for putting together this wonderful workshop, and I return the floor to you.
Thank you, Dr. Palmer. Great. It's now time to introduce you Professor Fortino, Chair of the IEEE Systems Man and Cybernetics Society, Italy chapter. Please, Professor, the floor is yours.
Okay, thank you very much for inviting me. I will be very short. Okay, so as you may know, I'm the chair of the IEEE Systems and Cybernetic chapter in Italy. Okay, so we were very glad to sponsor, your event that we deem to be very interesting, very topical on wearable systems and areas related to wearable computing systems, body sensor networks, because we were working on this subject since many years so far, more than 15 years so far. So I'm very glad that, the TPC and the organizing committee is with is rich of people coming from body sensor networks, wearable sensors area, including also, my strict collaborators like Raffaele Gravina and others. Okay, so we think that wearable computing systems are pretty associated with human machine systems. And this is one of the main motivations because we strongly supported the workshop. We are also in a process of finalizing a book on human machine systems, and we will have contributions coming from the founders of this workshop. So this is just to witness that the topic is still very hot. Okay, even though it was launched many years ago, it is still very hot. It is, I would like to say, a basic technology for next generation wearable computing systems, IoT-enabled wearable computing systems. So I'd like to give you a huge good luck for this event, and I hope that attendees will enjoy. I'm sure they will enjoy your workshop. Thanks a lot.
Thanks, Professor Fortino. Then is the turn of Professor Schena, colleague and friend of mine, and IEEE Sensor Council Italy Chapter Chair. The floor is yours, Emiliano.
Thank you, Carlo. I'm trying to share my screen.
Yeah.
Okay.
Yeah, we can see your screen.
Okay, probably now you can see my screen, correct? Okay, great. Hello, everyone, and okay, it's great for me to be here and present why the Italy chapter of the IEEE Sensors Council is sponsoring this interesting workshop focused on wearables. Actually, I'm one of the co-founders and now the chair of the Italy chapter of the IEEE Sensors Council. And before starting the presentation focused on this chapter, I really want to thank Carlo and Professor Bonato and Professor Vadarajan and all the organizing committee for putting together this great workshop and for involving the chapter that I'm chairing in this workshop. To better understand why our chapter has been involved in this workshop, I'll start with a short description of the chapter. It's one of the 28 chapters of the IEEE Sensors Council and the third founded in Region 8, which includes Europe. An IEEE chapter is basically a technical subunit of an IEEE unit, in this case, the IEEE Sensors Council. And this unit was founded with the aim to serve the sensor community with new publications, conferences, and technical committees. And its fields of interest and activities are the theory, design, fabrication, and application of devices for sensing and transducing physical, chemical, and biological phenomena. And of course, the wearable systems and wearable sensors are strongly related to all these topics. Well, along these 3 years, our chapter has followed these aims and have experienced a significant increment of members. And also we have organized several activities, among others, several awards, lectures, IEEE distinguished lectures, student hackathons, 2 of them focused on wearable systems, and the summer school. As you can see in my slides, this year we organized the summer school focus on wearable sensors in sport, and we are trying to organize the second edition of this school for the next summer. Well, thanks to all these activities, the IEEE has conferred 2 prestigious awards to the chapter as Best Italian Chapter 2 years ago and the Most Innovative Chapter last year. And well, when we after the foundation of the chapter, we firstly try to organize our subunit in a taxonomy based on 3 pillars, based on the sensors application, on the measurand, so the parameter that is measured by the sensor, and on the technology used to fabricate the sensors. And we try to involve other colleagues by funding technical committees based on specific topics. Now we have 22 active committees chaired by colleagues very expert in these specific topics. And if you take a look on the committees, it's clear that maybe all these 22 committees are strictly linked with the topic of this workshop. Indeed, almost all the technical committees can be considered related to the field of wearable systems. You can see technology exploited to design wearables, for instance, fiber optic technology. You can see type of sensor used to instrument wearables as ultrasound sensors, radar sensor, soft sensor, inertial measurement unit, and so on. And you can also see several applications in which the use of wearables can be important as application in biomechanics or in physiological monitoring. So we also have a technical committee that is chaired by Carlo, by one of the organizers of this workshop, that is focused on wearable sensors. The committee is Wearable Sensors Committee. And well, I think that the link now is clear, and between the topics of interest for our chapter and the topics of this workshop. And so this motivated our involvement in the organization and in supporting the activities of this workshop. So I finally want to thank you again, and to thank all the organizer, not just for this kind invitation and for the involvement of the chapter in this workshop, but to putting together this interesting workshop. Thank you very much.
Thank you, Emiliano. And give me the opportunity to share the last slide. And last but not the least, it's time to the IEEE Young Professional Representative. And today we have the Vice Chair, Vincenzo Randazzo, who I sincerely thank for being here today with us. The floor is yours, Vincenzo.
Okay, good morning, everybody. Are you able to hear me and see me? I hope so. Okay, let me quickly share the presentation. And let's see. You confirm everything is okay in the whatever. Okay, so good morning, everybody. As Carlo said, I'm the Vice Chair of the Young Professional Affinity Group of the Italian section, and I'm very pleased to co-sponsor this event, which is the second year actually which we work together with the WSAIM committee, and we are pleased to have an event within this workshop, which is the pitch competition this year, and that's gonna be tomorrow, by the way. Hope you have already registered. We have had already 15 candidates. Now application is closed, so you cannot do that anymore. So we're gonna see tomorrow who's gonna win the award. That is, let's say, given by also the Sensor Council, which helped me do the workshop. Okay, but very briefly, what is the Young Professional? Okay, first of all, the committee, I'm the vice chair, the chair is Federica Battisti, then we have the secretary, Elisabetta Mesiello, and the treasury Starity Committee. You find all this information on the internet. I just reported it for, let's say, sake of completeness. There is also some, let's say, general email groups that goes worldwide, so you're gonna be answered by maybe region 1 or someone else. And but again, what are the young professionals? Young professionals are basically IEEE members. We have already graduated from no more than 15 years and belong to an affinity group that is a non-technical subunit of a region. So, for example, the sensor, as was said just before, the sensor, the sensor section is a subunit with a specific topic it works on, while an affinity group is a, let's say, more general group in which there are different people from some different, let's say, backgrounds that are, let's say, in the same pool, let's say, are put together because they are graduated from 15 years and want to expand their professional goals and professional career. IEEE is free of charge, by the way, so you can really apply. Once you register in IEEE, you can also flag it and you become a member. And why a young professional? Because after maybe you got graduated while you work, I'm a postdoc, so you want to get involved, expand your global network, connect with peers, stay technically, so they can compete, and so on and so forth. At the very end is about, let's say, be in the middle and expand your network, expand your experience, expand your skills, and maybe give back some to the community at the very end. Because the very high-level goals is that we believe as IEEE, as IEEE and as young professional, especially in Italy section, the sum of the whole is much more than the doing it alone. So believe us, it's join the program and, let's say, stay connected with our activities. You can also organize your own activities. I mean, you can ask us to sponsor your own activities. How? There is a simple procedure. You just propose us an event, we work it together, and we deliver it. For example, we did this award for this event, or you can imagine much more complex event. workshops like this one, and so on so far. And finally, and I close the presentation, also as a student branch, remember that once you finish, you can become a young professional and continue your path in your career within the IEEE young profession. So thank you for your attention, and that's it. And enjoy the workshop, of course.
Thank you, Vincenzo. Thank you so much. Now it's time to start with the first speaker of the workshop. It's my great honor to start with the first plenary speaker of the workshop and of the day, for sure. Professor Subhas Mukhopadhyay, Professor of Mechanical Electronics Engineering at the Macquarie University in Australia. His field of interest includes smart sensors and sensing technology, instrumentation techniques, wireless sensors and network, Internet of Things, mechatronics, robotics, health monitoring, and etc. Among the numerous editorial duties is Distinguished Lecturer of the IEEE Sensor Council. In his talk, Professor Mukhopadhyay will talk about recent advances of sensing technologies, embedded systems, wireless communication technologies, nanotechnologies, and miniaturization that make possible the development of smart medical systems to monitor activities of human beings continuously. To all the attendees, the Q&A tool is now open for questions. Please remember to write your question here. And the floor is yours, Professor Mukhopadhyay. Enjoy the talk.
So I would like to share my screen, Dr. Carlo.
Yeah. You can.
Okay. Can you see my slide?
Yeah, I started screen sharing. Yeah.
Okay, so as Dr. Carlo mentioned that more than 700 people have registered and people are from different parts of the world. I'm really very, pleased to see that 66 countries are representing in this workshop. So I would start with good morning, good afternoon, good evening to everyone who are attending this workshop. So thank you very much, Dr. Carlo, for the invitation, for delivering these research activities, what we are doing. And I'm sorry that I had to change my time because I'm now based in Sydney and we are going to be almost 10 p.m. in the night. And also it is very pleased to see my friend, Professor Giancarlo, was presenting his chapters and we know each other for many years. So thank you, everyone. So it's my pleasure to share some of our research activity. So the title, Trends for Wearable and Medical Devices. So I'm based in Sydney. My university called Macquarie University. Our university is not very long history in engineering. We started late 90s, but in terms of technical contribution, it's quite significant. As you can see, our professors, Professor David Skellan and Professor Neil Oest, in late 90s, they were part of the invention of Wi-Fi. And of course, we all know during this COVID-19 and also during our day-to-day life, without Wi-Fi, the life will not be the same. So our university established in 1964, and we are just 195 in the international ranking, and we have around 40,000 students and around 8,500 international students. The number has taken a hit due to this COVID-19 pandemic for last 2 years. Our group, we developed different types of sensors, specifically for healthcare applications. Many sensors we need for different other applications, but sensors are fundamental for our life. If we want to improve something, we need to know what is the current value, and sensor gives us the value, the measured value. And that's why Lord Kelvin told that if we cannot measure it, we cannot improve it. We also see different medical devices. which are very useful for monitoring our health parameters. Some of the devices we can have at our home, for example, body temperature, or heart rate, blood pressure, those can be at home, but many devices, as we see here, we can see only in the hospital or clinic, and we use them when we fall sick and we need medical attention. In our group, in our labs, we develop sensors, and also we use ready-made sensors available in the market, interface them, measure the data, and put the data in the cloud. So we do in two different ways. Either we fabricate sensors, or we can make the sensing systems from readily available sensors. So wearable sensors are now becoming very important. Wearable sensors are basically sensors which measures our physiological parameters, process them, and of course it tells them whether the person is healthy or if there is some issue. And sometimes the wearable sensors are also known as wearable gadgets, wearable technology, or just simply wearables. Last 30-40 years, due to the advancement of semiconductor technology, processing speed, as well as development of new materials, lightweight and high powerful wearable sensors are now in use. And we can see them starting from the leg to our head, it can be used. Sometimes the sensors can be also implanted, that means is inside our body. We can see different types of sensors, starting from a simple thermometers for measuring the body temperature, and can be complicated electroencephalogram, EEG, and it can come either in the form of smartwatch, or it can be in the form of different badge or wearable clothes. Depending on the complexity, we can see in different forms. In terms of the applications, there are different types of applications, whether just to simple monitoring physical or psychological stress, and complex like evaluating concussions. There can be different types of applications. In fact, the wearable device has gone to a certain stage that it came as a joke a few years back, that if Olympic participants don't use wearable sensors during his or her training, it's impossible to win a medal. So this wearable technology, what we see in last 10-15 years, in terms of the research, has grown exponentially. Now, in 2020, 2021, we do not see that many papers, but what we could see, the result of the research, what has been done, has now been translated into products. So we can see different types of products now available in the market. Of course, still there is a gap, and that gap, due to some factors, the cost of the wearables are coming down, but still not affordable by many countries. But not only the cost, also sometimes people might be skeptical about the positive applications of the wearable devices. So that gap needs to be bridged, and we hope with time things will be much more better than what we see today. There are some, of course, challenges. In the last 10 years, in terms of the speed of the systems, Wi-Fi, display, video, we can see the quality has improved significantly. But one of the biggest problem what we can see now is the battery improvement has not taken place that much. It's only 2.2 times. That means with the same size, the power has improved only 2.2 times in the last 10 years. And the battery is one of the issue for extending the lifetime of this wearable device. Though there are some research going on, harvesting energy from body, but still it's not big enough for maintaining the operations and also communicating this wearable device for a long time. We are working in this area for last 15 years. This is one of the first prototype we developed. In the beginning, we thought it will be only for situation where we need help, especially for elderly people fallen down. We have gone improving it for measuring the parameters, for example, body temperature, heart rate, as well as other parameters, so that not only the fall, but also it can monitor the normal situation. And then we have improved to further to determine the emotion of the persons. So these emotions taken from the simple parameters, body temperature, heart rate, body conductance, and by simple classification technique, we can find out the simple emotions, whether the person is happy or sad or angry. And the care can be provided at that situation. Now, when we think of making a wearable device, the fundamental blocks, what we need, I'm showing here. We need the sensors, which is of course sensors designed and developed for wearable applications. We need some processings, smart embedded controller, which is interfaced with the sensors, processing the data at the node end. And then of course, after the data is processed, we want to either transmit it wirelessly or we want to upload it into the cloud. So we need the internet connectivity for making it IoT-enabled wearable device. And when we put our data in the cloud, we always need to think of how can we make the data secure. So security is very, very important for anything related to IoT. So these are the four fundamental blocks for making any wearable device as IoT-enabled wearable device. Few years back, there was a survey on the wearable device, and it's quite interesting to see that even people use the wearable device 26% during their sleep time. So that means those who are using wearable device, 1 in 4 persons, they use the wearable device during their sleep. Most of the time, what we see that people use wearable device during exercise. So people like to do exercise, they need to know how many steps they do, how many kilometers they have walked or run. So that's very common. But there are many other applications where we can see wearable devices are used. When we make this wearable device as a wireless device, that's the situation most of the cases. If we follow certain IEEE standard, we might need to use either Bluetooth or Zigbee, Wi-Fi, WiMAX, and these days, LoRaWAN, long range wide area network, is becoming also very common. So for example, body area network, Bluetooth we find very, very common. Each one has got its own range and own data rate. Most of them, except the LoRaWAN, they operate close to 2.4 gigahertz. LoRaWAN, of course, depending on the country, either it can be 868 megahertz, or like in Australia, we use at 915 megahertz. I will touch a little bit on our earlier work on smart home. The purpose is to make safe, sound, and secure living environment for anyone who want to live independently at the house. As we all know that people now live much more longer than before, but still at old age, people need helps for their day-to-day activities. So wearable device as well as non-wearable device in combinations can provide an environment which will be safe for the elderly people. And as we can see, the number of people living independent lifestyle, both in men and women, almost 1/3. And that makes us believe that this system is required for keeping them safe. So we started working on wearable system, wearable device, but then we extended it to making it non-wearable so that we can cover both wearable and non-wearable. And the reason for doing so is that sometimes it is very difficult to convince people to have the wearable device on their body. And in order to include those people, it may be good that they are monitored without even wearable device. We can monitor them using non-wearable device. The idea here is that we can monitor the activity of the persons using the smart sensor. So whatever the person use, those appliances can be detected by the sensors to see whether the devices are used. So we develop different systems using readily available sensors, or we also develop sensors to make a complete systems. And we applied those sensors in a old home, making the old home as a living lab. So that sensors, what we have used are different types. Some of them can be pressure sensors, electrical sensors, and also can be movement detector, like simple PIR sensor, passive infrared sensor. So here we see one volunteer living at that house and monitor continuously. If we have a situation where the person has got some hobby, it's quite useful that we can monitor the person very easily. These sensors all are based on Zigbee-based sensors. Zigbee is one of the wireless common transceiver. It was very popular in around 2010, early 2010. But these days we do not see so much application of Zigbee, but we use extensively using Zigbee transceiver. And the interesting thing is that here we do not need any microcontroller for interfacing the sensor. So when we talk about the technology assisted home, effectively we have the sensors. That sensors are plugged to any devices which we want to measure its usage appliances. And those sensor data are measured real time with timestamp. We acquire the data, store the data, analyze the data, and we determine the activity of the persons. That activity tells us throughout 24 hours how well the person is leading his life. So that's the main thing. Once we have the sensors designed and used, then mainly it comes down, how do we process the data? So the data processing requires different intelligent algorithm, and they should be smart and adaptive. So we need different types of algorithm as a part of this system, whether that is based on probabilistic approach, or that is based on time series, or some kind of pattern matching. So it's the combination of all of them. And the big picture here is to determine how well the person is. If we take the problem from totally computing point of view, we can tell that we are basically detecting the behavior of the persons. But we do not want to say it's the behavior, it's basically the person's life. So how well the person leading his life. So wellness determination of the person. Type of sensor depends on the persons. So it's a subject dependent, how the subject lead his life, and two subjects will not be the same. So type of sensors depends on the subject. And after selecting the sensors, it might happen that some sensors may not be required for a certain person. So we can eliminate the sensors based on the frequency of sensor usage. So if the sensor is not used very frequently, we may ignore or we may not include that sensor. So once we have the data, we can collect and we can tell, after annotating the activity of the sensor, we can tell what type of activity the person is doing. And then we can define wellness of the persons in analytical form, how well the person is living. And it based on two types of calculations. One calculation based on inactive usage, that means the sensor is not used for the day-to-day life. Another will be based on over usage. And we start with the 100%, that means the person is doing very well. And then it's slowly reducing. And we can set a value, threshold value, when we send a warning message to the caregiver. So that works very well. And also we can use the data which we are collecting and we can analyze, we can say how we can predict the future, the trend of the lifestyle, how the lifestyle is changing with time. All these things can be predicted about the persons. So that's very, very important. And that can also tell what type of problem is creeping in the person's life, whether we can prevent anything at the early stage, so which is very important. And if we could do that, we can actually significantly reduce the healthcare cost, which is very important. So here there are some results which we can use for predicting the person's life. Now, the most important thing is that whenever we have a monitoring system, whether we use mainly wearable sensors or wearable cum non-wearable sensors, what will be the architecture for that type of system? So the architecture what we are proposing is that we monitor and we collect the data 24/7 using wearable as well as non-wearable, and we put all the data in the cloud, of course with proper security. And then we analyze for the post analysis and visualization, but the data need to be in the cloud. So that's very important to know. Of course, this can be a debate whether the cloud will be safe, but we do not see any other way of having a complete system. This is, of course, it's just a concept, it's not still foolproof. And what we can see that these days people use smartphone, and if they use the smartphone for monitoring their activities, this is one of the simple example. There are different types of apps. These apps just monitor how many steps the person walk, how many kilometers. So you can see the daily, weekly, monthly, and also yearly. So this is one of the things which we can see is available now with us. And it only monitors how many steps the person does. But if we include all the other activities, then we can actually see 24 hours, 7 days, what the person is doing. Of course, there will be some issues, the privacy, but that will be dependent on the particular persons. I'll just touch a little bit on our current research activities. So we develop sensor, as I said, that we also fabricate sensors. Most of the time, our sensors are interdigital sensors, which are very useful for using on the body. In the beginning, we started making in the MEMS-based. As we can see, these sensors are 50 micrometer of pitch length. We also developed closer to this, like 5 micrometer. But in recent times, we are developing only flexible. And we developed some coating material for selective detection. So we call molecular imprinted polymer. And this is the artificial selection, and that can give us long durations because we can store it with normal situation, that normal temperature and so on. Making this polymer is a little bit complex process, but once we develop this polymer, the usage is very simple. So we have got some applications. This one, as we can see, is monitoring the contaminations from plastic bottle. Also, this is something for early detection of osteoporosis. This cannot come as a wearable. Of course, it can come as a wearable if we use the sweat, but this has been developed based on blood. So it's a medical device. And whenever we measure, the data will be uploaded in the cloud, so it will be visible to the general practitioner. So osteoporosis is a common disease in many countries. In Australia, over almost 5 million people are suffering from that. So it's a big problem for the government because huge amount of money is used for the healthcare. So the applications what we have developed, we can compare the result, which is quite close to the actual result tested from the laboratory, and we can see that we upload this data as a time basis, which can generate a warning message if the amount of CTX, which is the protein CTX1, C-terminal telopeptide, is large than the normal value. And few years back, we were thinking this can be a concept that the toilet will be smart toilet with some sensors, and the sensor will measure from the urine the amount of the CTX1. And interestingly, I could see that there are some research going on in this domain. Already some paper reported in the IEEE Sensor Journal, not published yet. So that's quite interesting and heartening to see that. So currently we use flexible material to develop different types of sensors. Last few years, we're working on that. And one of the interesting comment here I want to make, that for the fabrication of the flexible sensors, any university does not need high-end infrastructure. So that's very, very pleasing that with little infrastructure, it is possible to develop flexible sensor. And the flexible sensor is a very good candidate for making wearable clothes. And as we can see, the change of dimensions will give us another extra parameter for measurement of the strain. So it can be very good for the wearable clothes. And that's what we do. So for fabrications, depending on the situations, it can have a buffer either coming from PDMS or PET or polyimide film. And it will have the electrode, either carbon nanotube or the graphene or alumina. So depending on that, we have to choose the material for the buffer and the material for the electrode. Each one has got its own advantage and disadvantage. So over the years, we have developed different types of flexible material-based sensors for healthcare related applications, as well as some of them can be used as a tactile sensor for robotic applications. In recent times, we are also working on the EEG. So basically, it's EEG mechatronic interface systems, and it's in the preliminary stages. This year, one of my students in the final year project started this work, and we can see the idea is that from the brainwave, we want to control the mechatronic system. So this is research going on. And also, we have some other work on EEG, how the music can change our brainwaves. And interestingly, we have seen that music has more effect on women than men. So that's the interesting observation. One of our work, we are trying to put the sensor inside the body, implanted sensors, especially for addressing the back pain problem. So this is lumbar interbody fusion. And as we all know that the people who are suffering from back pain, if they go for operations and the doctor, they try to use the interbody cage with screws and other metal, there can be some mechanical problem, screw may lose, there can be misalignment and so on. So there are a lot of issues the patient can face after the operations. As you can see here, the screw came out, screw loose, the misalignment, all this problem. So the whole idea is putting the sensor inside the interbody cage. We want to see how the stress is distributed with time and whether we can get informations from the inside the body, how it is healing. So that's the whole idea of this work. And we have fabricated the sensors, and we are still working not inside the body. We are simulating the environment, and we are doing experiments. And what we can see, this sensor with a very tiny sensor, 2 millimeter by 2 millimeter, and we need arrays of sensors, and it gives quite good result. So we already lodged a patent in Australia, and we are working to make it the trial inside the SEEP, maybe middle of next year. So that's the work we are currently working on. This type of application also we need to consider security, especially when we have the wearable data putting into the cloud. Though security is not our main research, but we have people who are looking into the security, how we can make the security of this data so that there is no issue on this type of applications to make it foolproof. So effectively in our lab, we develop different types of sensors, both wearable and non-wearable applications. And these days we are more focusing on the flexible material to making the sensors. And the flexible material also, we are trying to use large size of electronic skin. So one of the applications we are looking into that, how do we actually monitor the back pain by putting the large sensor on the body, not inside the body, on the body, so that we can monitor the spine alignment. The challenge for us is to make the large size sensor with high resolution and sensitivity. And also, how can we actually use the sensors so that we can be supplying the power without battery, so energy harvesting situation. And we are also working on the implanted sensors and making the sensors IoT-enabled sensors. So with that, I will stop here, and I'll be happy to take questions or comments from the audience. Thank you.
Thank you, Professor. Any question from the audience? Please write the question inside the chat or Q&A tool. Don't be shy. In the meanwhile, yeah, I have a question, and it's a technology-driven question. In your opinion, what's the main difficulty in developing such kind of flexible sensors? We have seen a sort of printed sensor for low back pain. What's the main difficulties or challenges?
Yeah, I think it's a very good question, Carlo. I think the challenge is not the fabrication. Challenge is the lifetime. What I mean by that is that if you fabricate a sensors, how many months you can make the sensors operating without any kind of bias, drift, as well as the response. So this is the biggest challenge, because the flexible material, they are really good, but with time, few weeks, months, they are not that great. So this is the biggest challenge at this stage. So what it means that you need to replace the sensors frequently, which people may not like. So that is one of the biggest challenge we have at this stage.
Clear. Thanks for the clarification. And we have a question in the chat. Can you explain further the wellness index that you calculate based on the use of the different electric devices at home?
So the wellness, what we have defined analytically, is not based on any specific device or specific sensors, but is actually based on the person's activities for the day. So for example, if we monitor the persons and we know the person is doing certain things which we are expecting the persons to do, that means person is doing well. So wellness is defined that whether the person is doing his activities at regular interval of time, which is expected from the persons. So now there are two types of wellness. One wellness is that we are not getting any information through the sensors how the person is doing. So that means, suppose you think of a situation where the person is not monitored by sensor. So how long you can wait to assume the person is still safe? So that is one wellness based on inactive usage of sensor. That means we are not talking about the wearable sensor here. If we can use wearable sensor, we are safe because we are monitoring the physiological condition of the persons. But we are talking about non-wearable sensor. That means person is not using any sensors on his body. So that is one. Another condition is that suppose the person is using certain device for a longer duration, and that is specifically is coming from the bed usage. So normal situation, you may think the person goes to bed 9 o'clock in the night and person gets up 7 or 8. But on a certain day, person is sleeping too much. Whether the person is not well or person is really has some issue. That can be medical issue, or that can be, many incidents happen. The person actually died on the bed. People did not know. So that type of situation we are talking about, the person is using too much certain appliances, which may lead the person is not well. So that's what mathematically we are defined that. And the whole idea is that when do you actually trigger the warning message so that the care or help will arrive. That's the whole idea.
Okay. Thanks for the answer. So we have a simple
Okay, so I have got one question in the chat that flexible sensor in a lab study. Yeah. So yeah, that's interesting. Now we are working. So we have a PhD student working on that. Yes, we are developing the sensor in our lab. In terms of the biocompatibility, one thing what we have done, we have studied the material, that whether the material is biocompatible and non-hazardous and can be used inside the body. But second thing, even though many material in the specifications they tell something, but unless you do test on your own and you actually make it approved by the university ethics committee. So ethics committee has two types of committee. One is before you do anything, we have to get the permission that we have done. But next, another is that we have to do a lot of tests, and then we have to apply the committee to approve for any kind of trial. So that's we are now doing, because next year, middle of next year, we want to apply the sensors in sheep. So we have a doctor who is also the co-supervisor of the student. So the biocompatibility coming from two, one is the theoretical way, another is the practical way. So theoretical way based on like we have used PDMS and silver. PDMS is the buffer and silver is our electrode. So we checked that, okay, they are biocompatible, that's good. But then we have to use and we have to see whether they are actually really good.
Thanks. It's really interesting to test the compatibility and testing human and animals.
Human might be taking some more time. It won't be too quick because before we do, actually, it will be very interesting to know this operations who unfortunate. I mean, some people they really need to get operations. This operation is very expensive. One operation in Australian dollar is $80,000. So the doctor who is the spine specialist, he does operations every day, 1 or 2 in Sydney. So he's very rich, but the thing is, even after the operation, the problem is not solved. So sometimes if the patient is unlucky, after 2 months, 3 months, they come and complain, and he has to go, because MRI scan does not give you full picture. So that's the issue. And if sometimes the screw get loosened, screw come out, you have to operate again. So that's the biggest problem. And that's what the doctor thinks that sensor might be helping to monitor the conditions, especially when somebody has these operations on interbody cage, which is a metal cage, and how the metal cage and with the muscle and they are adjusting with time, how the stress is distributed over the portions of the actual spine and the interbody cage. Those are the challenging things.
Yeah, thanks. So we have additional questions, but the time is running out. So to stay on time, I prefer to skip.
Yeah, I'll be happy if anybody contacts me over email. So yeah, we can communicate for that.
Yeah, there are all the information are provided in the website, and the emails are also shown in the dedicated page of each speaker. So feel free to question by email. Thank you again, Professor Mukhopadhyay. It was really great to have you.
Yeah, so I would also thank Carlo for arranging the time, and I wish the workshop goes very well. And of course, it's very pleasing to see the numbers, and I hope that it is a very good initiative to reach people free of cost this type of networking and research activities. Thank you very much, and wish you a good time. Thank you
very much for your great words. Thank you so much. It's now time to switch to our second plenary speaker, Professor Toshio Tamura from the Waseda University in Japan. Professor Tamura research interests include biomedical instrumentation, biosignal processing, telemedicine, telecare, home care technologies, and rehabilitation engineering. He's probably the most expert researcher in the world in the field of blood pressure monitoring. And in his presentation, Professor Tamura will talk about wearable sensors for cardiovascular monitoring, with particular emphasis on photoplethysmographic sensors and blood measurements. Again, I want to renew to all the attendees that the QA tool is now open for questions. Please remember to write your question here, and after the presentation, I'll read the question. And the floor is yours, Professor Tamura. Enjoy the workshop.
Okay. Thank you. And how should?
Yeah.
Yeah, can you see?
Absolutely, yeah.
Okay. So my talk today, thank you for your kind introduction. And my talk today is the wearable sensor for cardiovascular monitoring, especially for the photoplethysmogram. And just disclosure statement here. And so my talk today is just to show the introduction and then its characteristics of photoplethysmogram and three major applications of the photoplethysmogram. So the one is the pulse rate monitor, and then pulse oximeter, and mainly for talk about the blood pressure monitors. So the wearable sensor for the cardiovascular parameters in the you can see the ECG, heart rate variability, pulse rates, respiratory rates, and the blood pressure, oxygen saturations. So nowadays the smartwatch is very common, and from the smartwatch we can get any pulse rates, oxygen saturation, and respiratory rate and blood pressure. Also, we can get an ECG and heart rate. In that case, usually we use the crown and the bottom of the smartwatch, and from the two electrode we can detect the ECG signals and also get the heart rate, and sometimes calculating the heart rate variabilities. The other possibility is the smart shots, and maybe we can monitor the ECG. That actually for the normal standard 12 electrodes, just on the smart shots, and also the kind of respiratory lights, the system. And also the mobile phone was used, and the more common is embedded camera is used to monitor the pulse rates. So the RGB signal is collected and calculated to the pulse rates, and the mobile phone is used as a gateway. So nowadays, and several wearable sensors in the market, and the people just wear the sensors, also attach the sensors, and then this data is connected to the IoT cloud via mobile gateway. So from the IoT clouds, and the decision-making system is used and automatically classified the data is normal and abnormal. And if the data is abnormal and this data is directly sent to the hospital or the healthcare provider and the healthcare professionals. So the people are now interested not only for the wearable sensors, but also total system, IoT system for the healthcare monitoring. So the first thing they just show from this part is we can just summary about the photoplethysmogram, and then its photoplethysmogram is mainly described by the Hartmann in 1937, more than 80 years ago. But so now the principle is the same. So the light is this time in the light is emitted from the miniature light bulbs that the wavelength white light source and using to the skin. So from this skin and reflected and scattered lights detected by the photocells. And so this and the signal component is due to the pulsatile nature of the blood flow and pressures in the microvascular expand and contract with every heartbeat. So it lead to change in the relative blood volume. So the photoplethysmogram is in the just measure the relative blood volume. So that usually using the light intensity. So the technique is the two techniques, and one is the transmitted light. The other is the reflected light. So transmitted light in the light is emitted directly to the photodetectors, but reflective light is scattered, and reflected light is obtained by the photodetectors. So the principle of the photodetectors in the artery, the light is emitted from the skin surface to through the blood vessels, and like in the systolical phase and diastolic phase, we have two different volumes. So the systolical phase, we have a large volume, and in the diastolic phase, it's a small volume. So we just seen the two peak of the signals. So from the two peak of signal, we can calculate in the pulse rates. So the content of the signal is DC component and AC component. DC component contain the venous volume and also non-pulsatile component of the artery blood and the other tissue components. So for the AC component, and this component is fluctuated according to the change in the blood volume, and that occurs between systolic and diastolic phase of the cardiac cycle. So the data is and show the several factors that affect the PPG signal. One is the wavelengths. So we using now several devices using the green lights. And previously we used RI for the pulse rate monitors. But the red and infrared used for the pulse oximeters. And the next measurement site is one is the transmit light for the fingers and earlobes, and reflected light for the brachial and wrist. So the both are using, and but several the transmit light is little bit in the good accuracy compared with the reflected lights. So also the other factors in the contact force. So contact force applied to the PPG must be carefully controlled because it exacts a strong influence on the blood vessel stiffness. So it very much depends on the blood vessel stiffness and the pressure. So we must take care of the high good signal to noise ratio and data. So the most important the factors in the motion artifacts. So the body movement has some motion artifact. So usually the time and frequency domain signal are proposed mathematically and statistically. So the most pulse oximeter use and the accelerometer and the inertia sensors to measure the body movement and eliminate the body motion artifacts and then calculate it for the pulse rates. So the next factor is the absorption and penetration depth. And maybe there are several wavelengths used for the photoplatismogram. And mainly pulse rate we can now use in the green light, but look at the penetration, the depths of the different wavelengths. So the green is a little bit shallow compared with the red and infrared. So previously we used on the red light, so the penetration depth is very deep, and we can get several and the blood pressure informations, blood vessel information. So that previously we can use infrared light, but now people use the green light. Why we use the green light? And because of the high power illumination of the LED. So that gets the cardiac cycle difference between the systolic and diastolic, show the large variations. So compared with the green and the infrared lights, and the green light is large variations. But the measuring site is at some difference. So the green light is still shallow areas, but in the large variations, that gives a very better signal to noise ratio. So now as we talk about some variable applications of the systems. One is a pulse rate monitor. And the pulse rate monitor, maybe everybody now is very common for the smartwatch. We can, in the bottom of the smartwatch, we can find in the green LED lights and also the photo detectors. So the other application in the embedded camera and detect on the pulse rate, and they show the pulse rates. But actually it's pulse rate, but most smartphone or mobile phone said the heart rates. So nowadays in the pulse rate is very accurate, but it's some researches from the Bennett et al. And they are trying to skin tone and the body profile and also the activities, rest, deep breathing activity and typing, and some clinical metrics, heart rate variabilities. So this research compare with the commercial available devices and some research basis devices and the real heart rate obtained by the ECG. So the results show some the heart rate accuracy is very much dependent on the type of device. At the activities and during the rest activity, the accuracy is very good, but during the activities in the some devices in the accuracy is less than 30%. The tone, skin tone is not difference for the accuracies. So this is the result from the studies, and then skin tone is not so much different with the colors, but the error is almost similar at the resting stage and also the activity stage. So in the activities in the look, Apple Watch is the best in the errors in the 5 beat per minute, but others is something in the less than 10 beat per minute. But the mean relative error is shown during the rest in the most commercial available smart watch is the good accuracies. But in the activities, there is some significant difference in the standard heart rates. So the pulse rate, but if we use the pulse rate meters in during the rest, we can get a very good result. So the next result is the pulse oximeters, and the pulse oximeter is now very common in the anesthetic stage. Also, the all hospital this device is used for clinically. So the pulse oximeter is now it's become part of standard procedure in administration general anesthetic in US. So this is measure the blood oxygen saturation. It's just the respiratory functions. So no operatively or no invasively. So this using the two different kind of wavelengths. It is the 660 on the red lights and 940 in infrared lights. So in the blood contents and oxyhemoglobin and reduced hemoglobin has some dependency of the wavelengths. So we can in the 66 and of course the other parameters and the metahemoglobin also carboxyhemoglobin has some effect of this and the signals. So the calibration curve was used in so AC component divided by DC component of red wavelengths and also the infrared. So the modulation ratio is calculated. This is R values, and R value modulation ratio, R value describe the relation between the practical ratio of the red and infrared. And this value, this R value, this R curves in compared to the real arterial oxygen saturation, and this is arterial oxygen saturation, and this curve is corresponding to the pulse saturation of the oxygen saturation of pulse oximeters, and this value is just using the R curves and then get the real arterial oxygen saturations. So this has several advantages: non-invasive and compact and low cost. And clinically, this has the warning of hypoxemia and then increased patient safety. And so this device used, and there is the dramatic drop in the anesthesia death rates, and of course, and they reduce the caregiver workload. So this device is used this is wired on this is and not wearable but used for the finger oximeters. So some limitation of the pulse oximeter is, of course, in the motion artifact. That's the nature of the photoplethysmogram. Also, the pigment, skin, and nail polish, abnormal pulse, and the low saturation, ambient light, low perfusion, and the intravenous dye and anemia. Also, the irregular hemoglobin and carboxyhemoglobin and the monoxide the hemoglobin, also the methemoglobin, and so. So during the COVID-19, the pulse oximeter is used frequently. Yes, this is the best device to monitor for the breathing situations. So that from that the researches, we have some one paper said some limitation of the pulse oximeters. So the previous results show the skin tone is not much difference. For the difference of skin tone is no accuracy differences. But in this result, we can see the arterial oxygen saturation and the below 88 is abnormal. But even in the abnormal values, pulse oximeter show the normal values in the more than 93%. So that means this is the white patient is 3.6 inaccurate, but the black people is 11.7% inaccurate. So that means maybe additional post-market data to better understanding how different facts include skin pigmentation may affect pulse oximeter accuracy. So the other main issues we must concern about the medical approved device. So usually in the state and the most the device and use of the reviewed by the FDA and receives 510K clearance. That's the medical approved device. So that the pulse oximeter undergo clinical testing to confirm the accuracies. But the other device, over-the-counter device is just sold directly to consume in store or online and includes smartphone applications. So that is not gives for the general wellness or sports aviations. So not intended for medical use. So that's the one caution. So if we can use this kind over the counter device, maybe we must check the accuracies. So like in the Apple Watch it said not the oximeter, but the Apple Watch said the wellness, oxygen wellness. So that said the wellness device, not the medical use. We must take care of of course in our study show this and the value is mainly good agreement of the medical approved oximeters, but in maybe something happens, we must take care of this device. So finally, we show the cuffless blood pressure monitors. So the cuffless blood pressure monitor is now is very popular in the research field. So many people just working for the several studies, and the present status is one is a basic physiology study. So that case maybe how to get the accurate blood pressure estimations. So mainly evaluation of the pulse transient time. So pulse which area of pulse and the transmit we can obtain, or when how to get the pulse, how to analyze a pulse transient time or so on. So the accuracy that's stable is the important point. So now it's think about some kind of draft proposal of the standard and still some limitation. And the other is the people using the medical approved device to the clinical practice. So maybe everybody knows in the simple ways we must compare with normal and the high blood pressures. So we just measure the ECG and the PPG, and then if the pressure is normal, we can define the pulse arrival time from ECG R wave to PPG peak over bottom over the first derivative of PPG signal or so on. So this value is in the shorter at the high blood pressure. So maybe we can just measure the PAT and then estimate the high and the blood pressure values. So now we have the 4 different kind of the principles now. It's very popular and the principle of now. And the PTT is a simple way to compare with the 2 different measurement sites and then just calculate it in the pulse transient time. And this pulse transient time it changes for the blood pressure changes. So the other is they just show the pulse arriving time, but actually the pulse arriving time it's not similar as the pulse transient time. So the pulse arriving time is mainly pulse transient time and pre-ejection period. So pre-ejection period is the time elapsed between the electrical depolarization of the left ventricle and the beginning of the ventricular ejection. That represents the period of left ventricular contractions with the cardiac valve closed. So maybe we using the impedance cardiogram and ECG, we can precisely define in the pre-ejection period. But in the resting stage, pulse arriving time is more similar to the pulse transient time. So some researchers and they just use the word of pulse transient time and the when, and they use the pulse arriving time. So the other the data, so this is just only used for the pulse waves. So photoplatismogram wave itself. So this is just the amplitude of peak values and also the diastolic, systolic and diastolic values. So these peaks, these amplitude and times. So like in the systolic and diastolic peak between the 2 values, this is actually said the time delay between the first and third component pressures. And so this is proportional to the pulse pressure. So maybe we can just estimate T1, 3 values and depending to estimate for the blood pressure. So the other is the second derivative PPG. So addition to the pulse contour parameters, and we also use in the second derivative parameters like in the peak and time of A, B, C, D, E, and then it's combined these values and then estimate of the blood pressure. So other is the pressure and the first derivative of pressure used, and this is the 2 PPG and the baristocardiogram and phonocardiogram. So each peak is just correspond to the blood pressure changes. So our results show try to have some draft proposal of the standard. So the accuracy during the dynamic change and long-term stability. So the accuracy is more the resting stage is in follow the protocol ISO 810602, that the cuff-based device. So at the resting stage, and we compare with auscultation method with 2 observers, and actually 85 subjects, but we only did the 30 subjects. But so results show the relatively well error and the standard deviations. This is within the 5 ± 8 millimeter mercury. So, and most research said the very good accuracy at the resting time. But the other stuff and the most cuffless blood pressure monitors, we would like to monitor the beat-to-beat fashion. So, but in that case, how to evaluate compared to the standard device? So if we can use in the direct pressure monitor, it's no problem, but we can use for the auscultation methods. And in the non-invasive method, and that case, the dynamic changes, the estimation is maybe increase the blood pressure and decrease the blood pressure. So that is very, keep on, if once in the increase of blood pressure and the pressure values keep maybe around 5 minutes to 10 minutes, 5 to 10 minutes. So during that time, and the blood pressure is must stable condition, and during that stage, we can do a free measurement. And if the auscultation method and the cuffless blood pressure method, so we must wait 60 minutes for eliminating the influence of cuff inflations. So if we can use in the auscultation method, and this and the 3 times measurement, we receive just 1 comparison data. So that means in the like in the 6 minutes to during the 6 to 10 minutes, we can get only 1 result. So that means in that period, we cannot estimate beat-to-beat fashion. So we must consider the definition of the dynamic blood pressure in the system. So for stability, this is long-term studies, and this is ISO devices, ISO draft of the system, and maybe first the 5 hours and the 6 times comparisons, and then day 2 and day 3, 2 times comparisons. But this most cuffless blood pressure had no calibration, maybe at least 1 month, no calibration. So that case, the reference for the oscillometric automated devices. Otherwise, if we can use auscultation method with observers, it's very much complicated. So we better to use in the oscillometer. It's not still some always problem for the oscillometric device used as the standard device. But for avoid the complexity, and maybe we can use the oscillometric device, and the result is relatively good. But some subject is intercorrelation is not so good. So this is our result. So maybe we need to have several and standard the protocol of for near futures. So the limitation is if the blood vessel is very soft and large pressure change gives a large volume change. But the rigid vessels, even in the large pressure changes and blood volume change is very small. So maybe we have some and parameters of the stiffness or and some kind of age dependency parameters. So maybe further studies need to for the accurate blood pressure estimation with the different and stiffness of the blood. So the other clinical studies in the Actia devices, so this is some CE marked, and then this device has the 2 good criterion for the resting accuracies. And also there's some problem for the positions, and usually people use in the sitting positions, like in the standing positions, and the maybe gravity effect has occurred, and then this value is the accepted, half of them are acceptance rate or so. And other application for this device for long term 6 months record with two the different kind of measurement. So this first green part is one drug treatment. So that case in the historical blood pressure is decreasing, but diastolic is not. But second therapy is using the 2 different kind of drugs, and then this cases and both blood pressure is decreasing. So the cuffless blood pressure is a very easy to use, and so maybe some blood tracing is very effective for the effective of the cuffless blood pressure. So, but that case maybe we must consider about the accuracy of this system.
Questo cos'è, Frankie?
And also, okay, I'll finish a few more minutes. And also the BioBeat and the system is in the just compare with the direct blood pressure, and then this device is also very good agreement of the direct blood pressure monitors. So now the FDA approved and the 4 devices now, and the 2 of them are photoplethysmograph applications, and also the CE marked here the system. Now it's Korean and the FDA's try to watch and also the camera-based device for the system. So, and also the over-the-counter device in here. So how the perspective is wearable devices are practically easy to use to keep the quality of life. So, but either medical device or healthcare device, wearable device need to high accuracy and reliability and validity. So the other factor in this standard is important to maintain good quality of the device for the clinical practice. Sorry for little bit right. Thank you. Thank you for.
Thank you, Professor. Thank you so much. And I want to thank you so much for your presence here today. It's always a pleasure to see your talk. Thank you again. Are there questions from the attendees? Cannot see any question yet. But I have a question about what's your opinion about the future, about the continuous monitoring of blood pressure in terms of technology, if you have some suggestions, and applications, because we have seen interesting studies, quite in lab studies, and what's next, in your opinion, in terms of, I don't know, monitoring blood pressure in other completely different scenarios?
Oh, this is not a very good question. But now people use and optical also the direct pressure measurement and impedance or the ultrasound or the other stuff. But for the continuously and maybe it's the optical method has some limitations. So maybe the kind of tonometric method, of course, that's the very severe for the motion artifact, but maybe pressure should monitor from the pressure sensor. So that's the best solution. I think, but I don't know. It's maybe several people is still studies and also some the microwave or so on. But it's maybe the first stage is we can think about the accuracy of the blood pressure. Even for the healthcare devices, we must check in the accuracies. So that accuracy should the same as in the cuff-based or not. So for the long-term studies, maybe we must reconsider about the accuracy of the blood pressure monitor. So for long time continuous monitoring, maybe the tracing and the tendency of the blood pressure change is most important. So maybe the device and for check the blood pressure change in not exactly, but some tendencies, because if someone had some different little bit to change the blood pressure volume and they go to the home doctors or so on, so and the hospital, and so maybe it's better to use on the some discussion about standard for the accuracy and the reliability of the system. It's first, and then after that we can use in the optically or pressure. But my feeling is pressure sensor is the best solution to monitor the blood pressure. It's not a good answer.
Yeah, clear. The message is clear. If you want to measure the pressure, use a dedicated instrument to measure it. Talking about the different technology you have shown us, there is a question from the audience about any suggestions for overcoming or controlling the amount of pressure applied in the plethysmography devices. So what's your opinion? What's your suggestions?
So it's a very difficult question, and so.
Yeah, because there are different devices that measure PPG.
Yeah.
But sometimes even Apple suggests to measure the PPG at a sort of distance, 1 centimeter from the wrist, but no information are given on the pressure
Yes.
exerted by the sensor on the skin. So it's a very good question, Meg. I don't know if you have some suggestion or easily it's impossible.
Well, and so the photoplethysmogram is the nature problem for the body motion over the pressure, contact pressure, so on. So maybe it's if you can use several devices and maybe you found several different values. So that is some problems, but
yeah, probably there are some studies using force sensors just estimate the contact force.
Contact force, yes, right, yes.
But yeah, for sure, probably in the market only few devices use.
So the market is maybe the best way is to keep the same contact forces, and that maybe is and reliable the result for the blood pressure and so on. So, but in so far it's photoplethysmogram is some nature problem of the motion artifact and the contact force on the contact site or so on. So also the blood distribution is a very important factor, and so. But it's not a good answer. Sorry about that. Cario, no, the mute. You are mute, right?
Yeah, sorry, I was talking alone. No, yeah, it's the lunchtime, as you can see from the picture.
Okay, oh, okay, thank you.
Professor, for your interesting speech, and also to give interesting questions to the speakers.
So if you have some question, then please send the email to I will.
Absolutely. I remember I told the attendees that in the website, each speaker has a dedicated web page with the contact. So Professor Tamura, thanks for your...
Thanks for the inviting me and speaking the
It's always a pleasure.
current status of the blood pressure monitor. So I really think in the cuffless blood pressure monitor in the market, and so the good shape. Otherwise, if people using the cuffless blood pressure, no, the blood pressure is not reliable. This technique is just gone. So I'm very afraid of that. So thank you for inviting me to speak about the photoplatismogram studies.
Thank you again. Your talk was very inspiring, especially for young researchers. Well, this session is ended. The workshop will start in around 1 hour. In the second track, we will have a new track chair, Federico Parisi. And thank you, Federico, for accepting our invitation. That's all. Enjoy your lunchtime or breakfast or whatever you want.
Okay.
We are from around the world.
Thank you, Carlo, and see you sometimes.
Yeah, absolutely.
In on site. So, okay, thank you very much.
In the next conferences.
Next conference. Thank you.
Bye-bye.
Bye-bye.
Hello, everyone, and welcome to the second session of this workshop. My name is Federico Parisi, and I'm very pleased to chair this session. And before introducing our speakers for this session, I would like to remind all the attendees that you can ask your questions in the Q&A box, and I will read them at the end of the presentations. So our first speaker for this session, forgive me for the pronunciations and correct me if I say it wrong, is Dr. Atis Tuncer.
Correct.
That's correct, thank you. So Dr. Tuncer is a co-founder of Cambridge Battery Research, which conducts work on novel sensor for battery health diagnostic. She was previously a research associate at the Cambridge Graphene Center and the Center of Advanced Photonics and Electronics. Dr. Tuncer received her PhD degree in electrical engineering from the University of Cambridge, and the research activity focused on radiofrequency MEMS device, photovoltaics, and 2D material for high frequency energy harvesting and storage applications. Dr. Tuncer's work on graphene devices include transparent and flexible microwave, millimeter wave, and terahertz devices such as antennas, metamaterials, sensors, and absorbers, in addition to graphene supercapacitors. Prior to her postgraduate studies, she worked for Aselsan Military Electronics, Nokia Mobile Phones, Philips, and AT&T Laboratories Cambridge, focusing on low radio design for military and consumer applications. Dr. Tuncer, the presentation today is titled Wearable Energy Sources for Soldiers in the Battlefield. Dr. Tuncer, the floor is yours.
Thank you. Hello, greetings from Ankara, Turkey. Today I'll be talking about wearable energy sources for soldiers in the battlefield. But let me thank first to Professor Varadarayan, Massaroni, and Bonato for inviting me to speak here today. Firstly, the information that I'm about to present is unclassified and mostly open source. And I'm not affiliated with the technologies that will be presented here or the companies, except for Cambridge Battery Research. And so I will try to present you from the soldier's point of view, this topic of variable energy sources in a battlefield. And let me start with I think I have a problem with this. Yeah, so I'd like to tell you a bit about the typical soldier load that he has to carry in the battlefield. Most of the examples that I'm going to refer to are from the US military, because information is widely available on this topic. So a typical soldier would carry several kits, including his uniform, his sustainment load, personal equipment, protective equipment, and weapons, of course. And that would amount to about 46 kilos. And for a 72-hour mission, the batteries would take about 10% of his load. And this is quite significant because as a result of operating in austere environments with such heavy loads, there might be injuries. So this table gives you an estimated power requirement for a typical dismounted soldier, and the amount of power required for a 72-hour mission would be about 9 watts. But this is dependent on the type of the configuration of the squad and the mission and it can go up to about 60 watts, and the total energy required may be as much as 4 kilowatt hour. And here you're seeing a table of all the equipment he's carrying that requires batteries. They include night vision, communication equipment, and so on. There are many aspects of these devices that he's carrying that is part of his burden, his load. At the same time, when teams are given a choice to use a certain type of equipment, batteries are a significant decision-making impact on the mission. And for instance, in this particular exercise, special forces were given a highly capable technical equipment, and the kit was running on a battery that would last for 4 hours only. Therefore, the forces were to carry up to about 57 kilos of batteries for a 7-day mission, and that meant that they had to leave the equipment behind. This is, from an infantry point of view, the equivalent of leaving a machine gun behind, because they had only a few rounds of ammunition. And so this is a critical, decisive factor in the way a mission direction goes. So let's have a look at the typical soldier equipment. You will see a soldier would be carrying batteries, chargers, power managers, some networks like swipes, which allows West integration of some of these power devices, and some renewable energy such as solar blankets with them, or multi-fuel generators. And they'll be using all that harvested power or even from primary batteries on loads such as communication equipment, binoculars, night vision equipment, and so on. So this is a typical setup. We'll have a very quick look at what they are. This one is the conformable wearable battery, which can be flexed and put into a pouch or a backpack. It provides 148 hours of energy. It weighs 1.2 kilograms. This one here is a West wearable power management system, where battery chargers, batteries, cables, everything gets integrated in the West of the soldier, where he can remove items very quickly or connect them. And this system provides about 40% less battery load. So that's significant. And it can be attached to renewable energy sources like solar panels and AC grid, DC grids, and vehicle adapters. This is a typical university battery chargers they use. I must emphasize the fact that in the military, battery charging is a significant task where they had to allocate soldiers to do this for several hours and keep housekeeping of this. It's a big issue, and the weight is about 4.5 kilograms. It can take all sorts of chemistries and allow batteries to be charged on the go. Squad power managers allow the collection of energy from various renewable sources or vehicles or AC grid, and to be used on computers and communication devices in the field. So let me try to move this. The next piece of kit is the fuel generator. This type of kit can take all sorts of fuels, including dirty fuel, and provide up to 1 kilowatt of power. It's a bit heavy, but it's on the portable side of things, but it's an essential kit and on the go. So in summary, the power requirements for the infantry, especially for 72-hour sessions of exercise sessions, they need to, the soldiers need to manage the power available to them, including all the sensors, the laser, the night vision devices, and so on during combat for this 72-hour period before resupply. There's no resupply before 72 hours. And it is a huge logistic problem of delivering batteries, for instance, to squads. They, depending on the squad type, the squads might be carrying as much as 70 kilos, and depends also on the mission of batteries. So clearly it's a big issue. First of all, let's go back to the variable power generation mechanisms and see what kind of energy that's out there that the soldiers can scavenge from the environment. There's the ambient wireless energy, photonic energy if there is sunlight, and electrochemical from fuel cells, thermal energy, and all sorts of kinetic energy mechanisms that they can utilize. And so there needs to be a way of actually comparing these wearable power sources. And one way of doing that is defining a figure of merit that includes the efficiency as a function of the particular generator merit in question, multiplied by its ability to stretch and ability to bend, multiplied by some sort of power retention rate under these loads. So, but is this relevant for the soldier in the battlefield? What are the most important factors that affect his moves, his mission? And so this is a kind of question that needs to be thought of carefully. So if we look at some of the power density for power densities for variable generators, some of them are quite good, but when they are worn on the body, it's maybe they won't be able to produce more than milliwatts of power, or microwatts and nanowatts in some cases. This might be sufficient for some Internet of Things applications, for some sensors applications. For instance, if you look at the ambient power, RF power available, you'd see that it's in the hundreds of microwatts range. If you can scavenge that, you can power up your sensors and IoT devices. But what about the radio and the night vision devices? We need more higher power levels to be able to power them up. From the storage point of view, also, lithium-ion batteries, they provide, they have a high specific energy and volumetric energy density, so they're quite popular. So maybe it's best to look at, narrow down the flexible energy storage topic into flexible lithium batteries. And over the years, the developments have been quite positive. Some of the devices went from wearing metal electrodes to more stretchable or fabric type electrodes. And it's promising. However, is this sufficient? And how do we actually measure the figures of merit for these kinds of stretchable lithium-ion batteries or other types of batteries? Well, one way of approaching this is to define a figure of merit, which is areal energy density divided by the bending radius of curvature. So it will include then both its usability as a device to provide the right kind of energy density for the application, and also it will include its flexibility. So Here you're seeing the energy density versus bending radius for various devices, various flexible batteries. And so there clearly needs to be higher performance, higher energy density batteries so that they can be used in bendable phones, roll-up displays and such. And you can see that medical patch is probably within the vicinity of this. So you can provide for some sensors the amount of storage they need, but there needs to be more improvements. So going back to soldier power requirements, again, giving an example from the US Army, they've launched lines of efforts to deal with energy storage, power management, power generation and charging of batteries, all these different issues. And the aim is to make sure that the power doesn't become a critical limiting factor for soldier missions. And so I will explain a bit more the outcome later on. And they carried out some operational benefit analysis, and the result is that conservation and generation of power reduces load up to 30, such as the use of solar energy and use of conformable batteries that take in harvested power and trickle charge helps enormously. So there's also, it was found out that there is a capability gap in power generation. Soldier power generation lies between 100 watts and 1 kilowatt, and lightweight solutions already provide milliwatt watt range or up to less than 100 watts, but there is a need of power generating devices between 100 watts and above. And they've also found out that power literacy has an enormous impact in the way power is the way it is used. Power literacy, meaning understanding of power requirements for each equipment, and also the disciplined use of batteries is quite important. In some cases, they'd end up discarding batteries with still most of the charge available on them, but they had to make that decision based on some intuition. And so there needs to be some sort of a support tool to allow teams to make up their mind on the battlefield to optimize power. And I'm going to show you an example, not this particular piece of search that they've done the benefit analysis on, but another one. It's a Simulink type model that models a soldier power requirement. So with the components and the connections and the soldier activity presented as inputs, and the environmental factors such as ambient temperature, location, date, time of day, and so on, you can do some time-step simulations to predict system performance. And so when you define a scenario, you calculate your load from energy harvest, your sources from your energy harvesters, you calculate your current drawn by your loads, and you calculate your state of charge and voltages from the battery. And this kind of ensures the energy is conserved among all the components. So let's have a look at what a typical soldier activity power consumption needs are. It's a table. You're seeing that there are some communication devices and other types of devices here. And here on the right, you were seeing marching, camping, surveying, and then suddenly you can see the power requirement slowly goes up as with each activity, and there's an attack on the squad, and they react to it. So communication power requirement goes up. So this kind of pinpointing the exact activity power requirements helps resolve component states and power flows, and the user is presented with a state of charge of all the batteries, and they need to make up their mind whether to choose 3 batteries or 4 batteries or 3 batteries plus a solar panel to complete the mission successfully. And you can here on the right-hand side, you can see the total power consumption as the activities turn into an engagement, and suddenly there is a lot of communication and the 3 battery scenario fails. So that helps make the decisions on how many batteries to carry. So I'll give another example from the US Marines. They have tested a lot of interesting systems with kinetic energy harvesting systems especially, and waste power management, and soldier power and data systems, as well as solar panels. And also they have tested a squad electric power network. I'll talk about some of them, especially the backpack and knee harvesters are of interest. When they are on the move, they can use them and also scavenge energy from vehicles. And when they're in a static location, they can harvest solar energy using their photovoltaic cells. So going into piezoelectric energy generation, there's a potential to generate up to 67 watts of power with the in-shoe devices, and however, the actual generated power would be of the milliwatts range. So they decided that this is insufficient for most soldier applications and concentrate on more the backpack harvesting schemes. So here is a typical energy backpack harvesting system. It allows about 35 watts and above of power to be generated. It can actually run a radio without a battery when static, and just simply by pulling it by hand can provide that sort of power up to about 50 watts. And the mechanism here is basically a spring mass system. So the walking of the soldier, the gait, this places the backpack going up and down, and this linear motion will rotate this generator here and provide the power. So this is useful. The accelerative forces are reduced by up to 90%, and the risk of injury is reduced. So this is quite interesting from an ergonomics point of view. Another example is the knee harvester. It is again a mechanical structure of gears at the knee that works on the negative work of soldiers going, let's say, downhill walking, especially because the knees are basically braking mechanisms, so there's a lot of energy there, and it taps into that, and it weighs 1.8 kilograms, but the metabolic cost of this device is unknown. This was I can show you some of the parameters that they generate. It's about 25 watts when they're going downhill. So that at a walking pace, you can expect 10 watts. And system weight, 1.8 kilograms. So, and finally, let's mention solar panels that are conformable and or foldable. These are flexible SIGs devices, and they are providing 60 watts, or they can go up if they are rollable type devices, and they weigh less than a kilo, and they're very significant. Their significance will be shown in a few slides later in hybrid systems. So going back to the line of efforts that were launched by the US Army to solve the soldier load problem, the fuel cell is a solution, simply because it is more like a portable rather than a wearable. Especially this one you're looking at is, I believe, it is deployed in NATO forces worldwide. These type of fuel cells allow lighter weight because the cartridges deplete as they're being used, and they're submersible in water up to a certain degree, but they're under evaluation, especially the direct methanol fuel cell is of interest. And the way it works is that methanol is provided from a reservoir, and when it impinges on a catalyst on the membrane, it forms carbon dioxide and it's expelled. And then it goes through the membrane and splits into electrons and hydrogen ions. And again, coming into another catalyst and works with oxygen, producing water. So this reaction produces some water and heat and carbon dioxide. Therefore, it mustn't be left in unventilated areas. So there are various advantages of this kind of system. Let's have a look at one of the popular lightweight type fuel cell. It works on pure methanol, provides 25 watts of power at 1.7 kilogram only. And the interesting thing is it's very quiet, and it does replace 11 kilos of batteries with 0.7 kilos of cartridges. Although the methanol has to be pure, it has to be adjusted for arid environments with water and so on. And also remember that there needs to be water management in this kind of system. So it is very useful to have. Normally missions are 72 hours long, but for higher, longer missions, there needs to be an extension of the system. So here you're looking at specific energy, specific power, and the system, 25 watts fuel cell system is here. That's the 72-hour line. And you're looking at a hybrid system here, which extends the mission time by using batteries and solar panels. The solar panels were assumed to work 1/6 of the time. So that is fuel cells. And the second important line of effort was, of course, the energy storage issue. So the US Army decided to pursue lithium-ion technology as the right solution. Obviously, lithium-ion is still developing. There are silicon anodes, silicon nanowires, and so on. There's a lot of research going on, but the most important aspect of lithium-ion technology is the safety issue. They are prone to projectile damage in the field and during combat. And also, due to its inherent instability and flammability, they are prone to break into fire, and this has been seen in the civilian world. You've seen laptops, mobile phones catching fire on planes, and this is a known problem, and it is even more serious in the battlefield. So one way of understanding the perforation, the projectile damage, is to actually test these devices. So here, a pouch cell here is being fired a bullet, and they're actually using X-ray fast photography to measure the speed as it slows down when it goes through the layers. That piece of information is useful for simulations. And here on the right-hand side, you see the CT scan of the damaged layers. And this kind of information helps them simulate using finite element analysis of energy absorbed by different battery layers. So this can give you a better idea on what kind of innovation potential there is out there to actually protect the soldier from being injured from instances of projectiles directed at the battery. Here you're seeing that the kinetic energy is mostly absorbed by, it is mostly absorbed by the separator because it's ductile, and the rest of the elements like the cathodes and anodes, they are brittle, and they are as you can see, they are damaged and they're separated. The layers are separated here. So this is the kind of information you can draw from such exercises. So lithium-ion electrode degradation is of great concern. Here on the top, you're seeing layers of anode and cathode with the separator in between. So at high currents or low temperatures, and if you're producing fast charging, you're forcing fast charging on your battery, soon lithium ions are reduced to metallic lithium, and they accumulate and form lithium plating. And as you can see here, this may lead to dendrite formation, and dendrites may eventually lose contact, get detached, and they lead to dead lithium in the cell, and they are volatile, so they present a major problem. And beyond that, lithium plating and dendrites lead to capacity fade. So eventually, when dendrites contact the cathode going through the separator, they may cause a sudden failure, resulting in a short circuit. And you can see this, they've actually simulated, they have actually produced it under lab conditions. It can take minutes to hours to days, the formation of these dendrites. And so at Cambridge Battery Research, we are innovating non-invasive, non-destructive methods for monitoring the electrode condition before the sudden failure occurs. So I think we are almost there. It's the future warfare. What does the future warfare look like? This is from a NATO document. The future will be more intelligent, interconnected, distributed, and digital for warfare. So there are these emerging technologies within the next 2 decades, and disruptive and convergent technologies, which is a combination of these two. They will be changing the shape, the way the squads operate in the battlefield. For instance, the soldiers will be having digital twins and dealing with synthetic realities. There'll be more autonomous vehicles teaming up with squads to carry out missions. There will be the soldiers will be providing sensory data, situational awareness from the sensors attached on their body, and that will provide the big data to the command center. And at some point they'll be decision making by AI systems, and there's so much going on, and these technologies need to be available to NATO countries within a certain time frame. And these technologies include advanced analytics for big data, communications, advanced decision making, advanced sensors. And obviously, on the AI side, the most important thing is probably the human-machine symbiosis and other aspects of AI. On the biotechnology side, human augmentation with exoskeletons will help, and there'll be more sensory sensors on the body to convey data. And these are disruptive and emerging technologies of interest. So I want to conclude, but let's call it the next steps for innovation, because I think the topic is the conversation, as long as it's focused on the soldier and his burden of this load that he's having to carry in the battlefield, and the power, the crucial part that the power is really, really important for a successful completion of a mission. The soldiers need power in excess of 100 watts. We need to have wearables that provide that, and they need to be able to store it reliably, and also networking it between squad members. And there needs to be decision support tools to optimize the power usage when they're in the battlefield. And obviously, they need to have safe batteries that are operational reliably, and also they need to be safe still under really difficult conditions. And for the future, they need to, the wearables community need to provide the power requirements for emerging and disruptive wearable technologies. So this is in a nutshell what I wanted to say today. Thank you for listening. I appreciate that. And I'd be happy to take questions. If I can't answer them right now, I'd be happy to answer them via email. Thank you.
Thank you, Dr. Tuncer. Is there any question from the audience? If not, I have a quick question, since we only have a few minutes. Which one of these technology and like how do you think this military technology is going to impact the consumer market?
Are you talking about especially from the power generation side or the energy storage side?
Like the generation of energy from like wearable devices. Do you think that in the next years we will see this kind of way of generating energy also for the public, for customer applications?
Yes, I believe that it would be so, especially for civilian applications. I would think that the backpack energy harvesting would be an interesting one, because it simply works and it provides a lot of power. I think that would be of great interest. But looking into the future, I think there might be something else on the horizon which might be even more interesting. Is for remote applications. They are thinking of, they're working on laser charging of batteries from a distance. That is very interesting, and I think it might have a great potential, but obviously it is in the military domain right now, and we have to watch the stage for that.
Thank you very much for your presentation.
Thank you.
So now we will switch to the next speaker. Our next speaker is, one second. Okay, is Professor Valentina Camamilla from the University of Rome for Italico. Professor Camamilla received her Master of Science in Electronic Engineering from the University of Rome, La Sapienza, and her PhD in Bioengineering at the University of Bologna. She's currently an Associate Professor at the University of Rome for Italico, and the research activity focused primarily on increasing the resolution of human movements analysis performed using stereophotogrammetry, addressing soft tissue artifacts and anatomical calibration approaches, and on quantitative and qualitative technique and performance analysis in sports. Professor Camamilla serves as board of directors of the 3D analysis of human movement technical group of the International Society of Biomechanics, and she is also an associate editor of the Journal of Biomechanics, Frontiers in Sports and Active Living, and Sports Biomechanics. The title of Professor Camamilla presentation is Wearable Sensors for Sports Biomechanics. Thank you, Valentina. The floor is yours.
Thank you for the nice and long introduction. So my role now is to expand upon what's the use of wearable sensors in the sports biomechanics domain within the trend that tries to describe the impact of wearable sensing devices and in sport the potential to influence practice, providing actionable insights to practitioners is quite important. So I will drive you through, but let's first start on, you mentioned Foro Italico University. This is where I am now. And it's a university surrounded by sport facilities. In fact, it's one of the only Italian and few European universities only devoted to sports sciences. And so along this line, our laboratory, which is composed by several people, it's a multidisciplinary staff with physiologists, computer scientists, bioengineers, and motor scientists. And our perspective on sensors is that of users, intelligent users, but trying to exploit their potential for specific applications. So this is the perspective from which I will speak today. And assuming that human movement analysis might not be familiar to all of you, I will briefly introduce the general context and then shift towards describing briefly the sensors that are mostly used for sports applications and look more into the details of the perspective of sports. So the whys, what, where, how, and who. So I borrowed a W from how because the when is less important today. And then at the end, I will go back to wearable sensors in sports by the perspective of a systematic review, several systematic reviews of the literature, to see where the state of the art is at the moment. So let's start from the first step. So human movement analysis is interested into the quantification of movement and of the causes of movement, that is forces, kinetics. So the aim is to gather quantitative information of this kind to describe the musculoskeletal system behavior during the execution of a motor task. Why do we need to quantify human movement? There are several applications and domains. For example, in the clinical settings, we might be interested into defining a targeted intervention to devise a prosthesis, or in the surgical setting, navigate the surgeon within the joints is replacing or repairing. In the sport domain, the focus could be both to optimize performance or reduce the risk of injury. Of course, we'll speak a lot about sports, but in the general introduction, we can't forget economics, because improving the worker's safety can also go through measuring its movement to reduce the error rates, and of course, while protecting the worker, increase productivity and the quality of the work. So if you are not familiar with the system, I assume you may be, but if you're not, if I name motion capture, you think of the entertainment domain, it is full of motion capture systems, especially for special effects. Avatar was a milestone within the setting because the filmmaker was filming with a rendering of the motion capture system outcome. And it was the most complex so far, using motion capture for entertainment. What we do in human movement analysis laboratory is more related to quantifying accurately what's going on, but the system is the same. So a typical laboratory has a motion capture system made by several cameras emitting light in the red spectrum, in infrared spectrum, and receiving the light potentially reflected or emitted according to the systems by markers located on anatomical landmarks. If you're interested in the causes of movement, in forces, in the setting, you could have force platforms embedded in the floor that provide you with kinetics. The combination of the two information, kinematics and kinetics, can allow you to extract information on how the joints are moving, so joint kinematics and kinetics, movement that can be, moments that can be associated to the muscle activities. The rendering of this information can be in this way, not the other fashion type we've seen. And the thick joints can allow you to describe the joint activity or the center of mass activity. It requires a complex setting on the subjects, which gets even more complicated if we add electromyographic systems that provide further information about the musculoskeletal system. So you can understand that having the subjects set in this way and then ask them to just walk normally is not exactly what you expect to be an ecological setting. It is possible that all these instruments, as the previous talk highlighted, in a more dangerous setting, is not easy. Moving with all this equipment may alter the true object of the analysis. So although those are the gold standard instruments, it would be much better to go on field, have a very small equipment, and test the athlete performing his own task. This is an athlete, but the same concept applies for a clinical setting where physiotherapists and medical doctors might be interested in looking at the patient in a moving in a realistic way. So the question is on where is best to analyze a motor task. Is it better to stay into the lab or to take the lab onto the field? There's no single answer to this question, because having the motor task into the lab entails now measuring systems like the ones just briefly introduced, which provides accurate insights into what's going on. On the other hand, taking the lab onto the field, same task, different tools, video analysis, pressure sensors, provides the possibility to have an ecological setting, a real movement, a real scenario, a golf field, which is not feasible to have in the lab. So this introduces nicely the reason why wearables are becoming so important, although the laboratory doesn't lose all its power, as already mentioned. What are the wearable sensors that can be used, can be exploited in the sport setting? There are so many options coming from the miniaturization of electronics, advancing sensor technology, computer power, connectivity, and also the fall in the price of components. So out there we have heart rates, respiratory frequencies, sweat composition, pressure, temperature, a lot of sensors that have been mentioned and will be mentioned in these 2 days. But if we shift towards human movement analysis, biomechanics, the field narrows down to the sensors I'm showing here. So inertia sensors that can be or cannot be equipped with EMG sensors, activity trackers, pressure insoles, and GPS trackers. These last sensors are really spread, since wearing them on the trunk is not perceived as encumbrant, and several sports allow using this type of sensors during competitions. So of course, the regulation plays a role into the possibility of using the sensors during matches and competitions. Among all of these, if I have to say which are the most important at the moment, I would focus on inertia sensors without hesitations, although all others have their share of importance. So I will focus on inertia sensors today from now on. The market is full of possible systems, specifically targeting movement analysis. The sensors inside those devices may be the same as those sitting in your smartphone, but of course, those are arranged to provide movement analysis tools. So having in mind the final aims of movement analysis. So what's inside these sensors? Usually we have a combination of 3 families of sensors, and we have accelerometers, which measure linear acceleration, gyroscopes measuring angular rate of changes, and magnetometers. The first two take the name of properly inertia sensors. And if you only have these two, you would call them inertia measurement units. If you add magnetometers, you're speaking about MIMUs, so magneto-inertial measurement units. Why are them together? The importance of merging them together and having 3 sensors of each type, so having a 9 degrees of freedom sensor, relies on the fact that the combination is essential to obtain the most important information retrieved with sensors, that is 3D orientation of the sensor. To have 3D orientation with respect to a reliable global coordinate system, you need to have reliable and stable references. So accelerometers provide you with information of the gravity direction, which is vertical, and if you need to have the yaw, so the orientation in space, with respect above the vertical axis, you need to add a magnetometer that gives you a horizontal direction to follow. And this can provide you, after several operations to integrate the angular velocity and linear acceleration, can provide you with the orientation of the sensor in space. The type of sensor that is mostly used for human movement analysis sits in the upper corner of this graph. This is a nice image in the Passaro review, and shows that microelectromechanical systems, MEMS, technology provides a low performance, low cost ratio of biostability and scale factor stability. So we pay a cost in terms of quality of performance to have sensors that are really cheap in themselves. So what happens is that the market and the engineers are building countermeasures to the poor performance of sensors to exploit their potential. So from now on, I'll speak about MIMUs based on MEMS, built on MEMS. Let's look inside briefly. We have accelerometers, which are built on the reluctance, the inertia of a portion of sensor to accelerate linearly along a single line as a response to a force. In this case, the capacity changes due to inertia, and this relates back to the acceleration. Similarly, in concept, the gyroscopes embed a structure, a mass, which has a reluctance to accelerate about an axis. So in this case, the inertia to angular motion is used to measure the response to a torque impressed to the sensor while the sensor is rotating above this axis. You see in the slide. If we look at magnetometers, as already mentioned, they do not rely on inertia, but they're based on the Lorentz force, which relates to current intensity, which is measured to the magnetic field crossing this bridge that can be deformed through the action. So without getting into further details about the sensors, let's shift to sport. So what's the potential of MIMUs for sport? I see them as full, half full, and half full, because they are really full of potential, can generate a whole lot of applications, but they're also full of problems. And the limitations of the sensors depend on all the 3 sensors mentioned, because we have soft tissues wobbling around the participant, the athlete, pretty much as the harvester backpack we saw before. We have ferromagnetic disturbances affecting the magnetic field measures, and we have drift, especially for gyroscopes. We need to transfer the data, or we need to storage them, and the sampling frequency, of course, is an enemy in terms of data storage. So having in mind these sensors and these limitations, let's shift away from sensors for a while and look at the perspective of sport. Why do we want to measure movement for athletes? The perspective is that of performance evaluation, because we want to analyze specific details and we want to use them to provide a feedback to the athlete to target defects, which could lead to improvement. So anytime we need to select what to measure, we need to have a research question in mind and the performance model of the specific sport. Each sport has its own factors affecting athletes' performance, and those in black are the ones related to movement, which affect the way in which technique is performed, and sits on the capacity that each athlete has to perform: force, rapidity, resistance, flexibility. So you have a research question related to providing a feedback to the athlete. You might search in the literature for possible answers to this question, and you must be driven by the performance model. At this point, you can select among a long list of key measurable quantities, but of course, having in mind why you measure them. And these quantities start from looking at the different phases of the task, which have different aims. For example, in running, you have stance phase and flight phase. And within these phases, you can look at time and frequency parameters, the simplest possible, and the most accessible with wearables. And going complex, you can look at kinematic quantities like step length or progression, which potentially appear as simple, but cannot be simple because sensors measure acceleration. And as already mentioned, orientation is important also to describe the joints, because the relative orientation of body segments gives you a description of the joint behavior. Kinetic quantities are also important for description of a motor task because, for example, the braking impulse or the propulsive one are causing the athlete to decelerate and accelerate during his movement. So we have a whole list of potential quantities to be measured that can be associated with ideas and quantifications related to the specific question and sport. However, as already mentioned, we have limitations to this potential, and you see the red list here, which is not small, of the quantities whose reliable quantification is still limited using inertial wearable sensors. For example, instantaneous velocity, but also joint angles. You can get them, but their accuracy must be questioned every time and validated in specific settings. So to best exploit the potential, countermeasures needs to be applied both a priori and afterwards in post-processing. And I refer you to this literature for a detailed list, but I just quote a few that are mostly important. For example, the way in which the anatomy is considered is essential to track joints, but also fixing the devices on the body in the proper way is important because wobbling of soft tissues might completely destroy the information you're searching for. Others might be more general considerations for sensors. What are the countermeasures in the post-processing analysis? Several people, smart people, I would say, developed algorithms based on the knowledge of what is going on. If we know that the flight phase is vertical, then you can use this information to eliminate the wobbling you see here. Sensor fusion is also the key element to combine the information coming from different sensors and have a reliable orientation. Okay, so this is the how can we get the best out of limited sensors, but there's more important to the how, the ability to provide actionable insights. So how can we use this information to inform athletes and coaches? We can start from the simplest, providing visual feedback, which is simple for the user, but not necessarily for those that provide the quantitative information, to estimating specific movement-related quantities, for example, the elbow flexion here, which is considered an element of illegality in cricket, and you need to measure it accurately to protect your athlete from being disqualified. How can we combine this information to go from data to actionable insights? It is very important that we have in mind the value of the information so that we can provide practical value to information. And this information and the system related should be the simplest possible or the least complex possible to be used as a decision-making tool. At the same time, you need to know what to do with the information, and you need to be able to explain how it works, and to be sure that the system is valid and reliable. Otherwise, you don't have the appropriate level of skepticism in using the information that comes from sensors. Given this scenario, then you can call for artificial intelligence for help, because you have big data and you have plenty of potential algorithms to create predictive signals. But again, not disregarding the importance of AI, it is also very important to set a specific framework for the evaluation. So the knowledge that we put into the AI system will drive the future outcomes of AI. To provide actionable insights, you need to identify the correct form of a model task performed and deviations that are agreed within a clinical consensus as critical for the injury, for example, as in this example, for the anterior cruciate ligament injuries. Once you have this, you can expose sensors to specific movement characteristics of correct and incorrect performance. Because if you have this framework, you then can identify exercises as correct or not correct. And if incorrect, you can identify deviations. These are the elements to drive an actuation strategy. Because if something is correct, you can provide a positive feedback. If it is incorrect, you need to send corrective feedbacks. So this is the framework that specialists should drive design, plenty of a multidisciplinary scenario of model scientists, engineers, kinesiologists, bioengineers. A reference community for this respect is the International Society of Biomechanics in Sports. So now that the perspective is clear, and with the few minutes remaining, let's look back at the wearable sensors in sports, but then asking for help to the literature setting. As many other domains in the last few years, there's been plenty of systematic reviews going on, but of course there's also a lot of literature to be revised, and sports biomechanics is no second to other domains in this respect. To summarize the information, I'm using our lab contribution to this endeavor, especially focusing on sport performance evaluation, injuries, and sport for athletes with disability. There's more to it, but I need to keep it short. So in terms of assessing performance using wearables, in 2018, I would say that it's already old, because not only athletes run, but also the literature in this context. We revised 286 papers with the focus of assessing model tasks in the sport domain performed by athletes with wearables only. And we found applications for almost 50 different sports. 1/3 of them were cyclic, meaning running, swimming, cycling, or rowing. We don't know if because the cyclicity of the task simplifies algorithms or because those are most practiced sports. But they're important in this scenario. Another third is of team sports, but also you see in yellow all sports that are performed outdoor, wind sports, for example. So the wearability of sensors increase the possibility to explore these sports, the potential wearables already mentioned. Of course, there's a lot of possible placements and sensors and parameters extracted in this long list of applications, and also of devices that have been equipped with sensors. I can't tell them all, but I summarized them here. So half of the papers focus on technique analysis, because this is where human movement analysis can give the most contribution to providing feedbacks. But it also has a huge potential in match analysis, which is characterizing the intensity of an athlete's movement, focusing on him as a single point, center of mass movement in space. And also remember the sport model, sport performance model, the capacity of an athlete to perform sits at the basis of his potential. So assessing it is also important. And activity classification in 2018 was expanding, and I assume now we have at least other 60 papers in this AI related domain. If we shift to the other face of the coin, because performance and injury, of course, go along together, unfortunately, we can observe a similarly live scenario, 165 papers revised until January this year. This is work in progress. We see here that the literature focuses at the pre-stage, so analyzes the athlete before it gets injured most of the times, and looks at the athlete during performance to try to catch the risk while occurring, or in a limited number of papers at the post stage. Most of the studies try to assess sport-related risk of injury factors. A few set thresholds or monitor the devices or the athlete after an injury. If we look at where the literature sits, we still have cyclic sports and team sports, but most interesting, you see here that the overuse injuries in individual sports are the most investigated, because they have a potential to be prevented. And if we look further into the type of injuries, we see that the running has the most of the share. The research is still in the research and development stage, while the deployment of these systems in a TRL scenario is still in its infancy. I expect to see a lot of deployment of these approaches in the next few years. It is a smaller share, but still important and interesting in our perspective, that of athletes with a disability. Wearables allow them a higher potential to personalize training, to reduce their injury, and to classify them within a sports system that allow an equitable competition for athletes with a disability. This literature is mostly focused on wheelchair practice. Most of sensors are placed on the wheelchair, and also because measuring is easier, but also because the personalization of the assessment is very difficult for these athletes. So let's try to summarize before running out of time. What are the trends of the use of wearables in sports? What is mostly measured? As already said, technique of individual sports, in particular cyclical sports, is assessed both to enhance the performance potential, but also to prevent injuries. The model tasks analyzed are the cyclical ones, like running, rowing, and swimming, but also throwing and swing have a big share of interest, possibly because overuse of a repetitive movement of the upper limbs is important for injury, but also because throwing and swing are essential to performance. In terms of parameters, sensors are mostly used for temporal assessments, for kinematics and body segment and object orientation. Also because of the red light on other areas and parameters that are not reliable enough to date. Studies focused on elite and sub-elite athletes, the WHO, probably because we want to steal their secrets, we want to prevent them from injury because their injury rate is higher, but also because there's more interest and money into the elite sports. Competition and training field are the most investigated where and when, although lab studies are essential to develop this domain and validate measures, and they cover half of the papers we revised. Interestingly, the why spans different areas, but is still limited by the development of this research domain. So we see most papers describing technique or assessing sport-related risk of injury predictive factors but we can expect different whys to be explored later on when the information derived by sensors and also by the Internet of Things scenario will increase the predictive power of these sensors. And so far, for disabled athletes, performance in wheelchair sports has been assessed as a main topic, but I expect also here on a smaller share and expansion of interest. So what's next? Talking about expansions, I think the framework of the what's next is still always this one. So we have wearable sensors. They may change, improve their accuracy, but we have wearables and we measure movement-related data. We extract key information. KPI means key performance indicators, but we could also have key injury information. And we assess performance injury risk in order to provide a feedback to the athlete. So this framework, of course, sits on the tools of artificial intelligence in the different stages, especially in the last two. And they can be used to develop tools for technique correction, so give the feedback to the athlete of the appropriate technique for performance, but also provide real-time feedbacks of measures of injury predictive factors. But we need to know first which are the injury predictive factors. So literature trying to exploit data coming from sensors to predict injury risk are already out there, and you see ANN that plays the most role into this prediction. But there must be and there will be more studies in this area to have predictive factors to be exploited for real-time feedback. Both tools for technique correction and feedbacks for injury prevention are best exploited into a long-term monitoring scenario, because forecasting systems need to see the human body evolving through time and observe the increasing amount of load on the person, the internal load perceived, or on specific structures of the athlete's body. And also can take into account the periodization of training, which is not homogeneous through the season. And of course, it depends on the specific sport, how the season evolves. So long-term monitoring is essential, especially for injury prevention, but also to support the development of a performance. Last but not least, again, focusing on athletes with disability, this information that prevents them to get injured while allowing them to perform can certainly facilitate participation for these specific athletes. And so this is my what's next vision and also my last slide. And I only have time for thanking people that provided me with part of the material, the workshop organizers for inviting me, and you for your attention.
Thank you very much, Professor Camamilla, for your presentation. And now, if there is any question from the audience, you can write it in the Q&A box. And if not, I would like to start with a question. So, do you think that will be possible to like some of the elements you introduced, like the analysis of the performance and the prevention of injuries, would it be possible to achieve some of these points using off-the-shelf wearables? So for non-professional sport practitioners, for example, just wearing a very limited amount of sensor with conditions that are not very structured, so like a different way of wearing sensor, kind of like sometimes a little loose, things like that. Like, do you think it's something that is possible, or is still not?
Yes, my focus was on, and the literature focus is on elite sports, where a millisecond could make the difference in terms of the kind of metal of your metal. But it depends on which information you are retrieving. There's a lot of app for the smartphone, or sensors that you can wear like an armband during running, or for a cyclist, there's a lot of apps and devices that are out in the market for general practitioners. If you have a loose sensor, but you are measuring the number of strides per minute, the information is accurate enough to describe your pacing strategy, the time you're running, the heart rate integrated with the number of steps would provide you with an information of how much energy you're spending during your training. So there's a lot of information that is accurate enough to be exploited. For the general public, the big problem is not only the accuracy of the information, but also the use of the information, because you need to have an intelligent app that takes the place of a coach, which is not easy, of course, otherwise we would close our university and send our students elsewhere. It's very complex, the human system and the adaptation that the athlete has to the environment, his own status, for example, the sleep quality, or his mood, or the problems of the former training. So the problem is not only the quality of the information coming from sensor, but mostly what you do with this information. There is enough reliable information that can be already exploited, and possibly is not fully exploited for non-professionals, given that the interpretation is in the end of instruments that can carry a limited amount of intelligence within them. But also in this respect, I expect the market to grow, to develop applications for the general public that embed intelligence from coaches and from sport experts. I don't know if I
and like on that note, since we still have like 2 minutes left, I wanted to ask how difficult it is to generate supervised data, so like labels for training machine learning algorithms on this kind of data?
That's a very good question. We need to rely on coach experience. And for example, we are currently labeling vertical jumps into correct and incorrect to develop a classifier to be embedded into a smartphone application. And we are comparing the classification from several model scientists based on the description of the proper technique execution. And even in a so simple and standardized task, it is not obvious what is good and what is bad. So having reliable labeled data, it's a tough job. Even worse is to have injuries labeled, because it's much rarer that you have injuries, luckily. But yeah, that's a critical point for this development.
Thank you very much for your presentation, and I want to thank both speakers. So thank you very much for your contribution, and we will have now 20 minutes coffee break before the next session. Thank you, everyone.
Okay, good afternoon, everyone. Can you confirm you hear my voice?
Yeah.
Okay, I would like to introduce the session this afternoon for the WSAIM International Workshop, and let me introduce Professor Stefan Leonard. He received a Master of Science degree from SUNY at Buffalo, New York, USA, and a PhD degree in control engineering from TU Darmstadt in Germany. He also holds a MD degree from Goethe University in Frankfurt, Germany. He is currently full professor in biomedical engineering and RWTH Aachen University since 2003. His research interests include closed loop control and automation in medicine, bioimpedance, unobstructed sensing, and cyber medical systems. Professor Leonard is a fellow of the North Rhine-Westphalian Academy of Science, Humanities and the Arts at Düsseldorf, Germany since 2014. He's also associate editor of the Journal in Clinical Monitoring and Computing, the IEEE Transaction in Biomedical Circuit and System, and the IEEE JBHI Journal, among others. So I would like, therefore, to invite Professor Stefan to give us his interesting talk, and so the floor is yours.
Okay, thank you very much, and good afternoon, everybody from Germany. So I can, I guess, share my screen now?
Yes, yes, you should be able, but let me know if you are unable to share it.
Okay. So I guess.
Okay, I can see your screen. Maybe you can put in full screen the slides.
Okay, then this is on the other screen now. Okay, let's double check again. So now you should see the full screen, right?
Yes.
Okay. All right, everybody. Again, thank you to the organizers for inviting me to give this talk. And I'm very happy to be here and share with you some of our experience on the topic of wearables and body sensor networks over the past few years. Oops. This has already been said to a large extent. I may add that I've been a Philips chair for medical information technology. This was an endowed chair position from 2003 and to 2017. And some of the projects that I will present come from that liaison. Right, so I should start with the question, maybe a definition. What do we mean with wearable, really? And I guess you did already talk about this to a large extent, but maybe it's useful to also recall some of the categories involved. And then we will have some application areas covered, some of which we have done ourselves and some of which come from the literature. And I will then go towards body sensor networks and also introduce our research body sensor network. So if you look in the internet and try to get a definition from that, and I put here some German definitions from the internet with also the URLs, but I'm also trying to catch the significant keywords that come with that. And this one says that when we talk about wearables, it's all about computers which are body worn at the head or the body. Here we have another one where it says it is about vital sign monitoring, about pulse, motion, fitness trackers, glucose, and blood pressure. And we have a third one where it says that we have computers with sensors connected, attached to the skin, sometimes implanted, and there is radio connection. And I guess all these buzzwords, these keywords already define, or at least help us define what we think what a wearable is. This is a growing area. We have lots of examples by now, commercial ones, and they come in various shapes, and it is obviously a growing market. Now, I think if we look at components, then we can say what we have already heard, there are sensors. There's a microcontroller, a computer, there is radio communication, and what we have not heard, there is power supply. And last but not least, we should not forget, often wearables also have or are actuators. And I give you an example of that as well. So this is a prominent example. It's not a medical or not per se a medical example, but of course, smart glasses come to mind. Many people think if you talk about wearables of these glasses, there is a new one just recently launched, and there has been one around for some years. So that is one option. Smartphones, of course, are a prototype of wearable and have a long history by themselves with shape changes and, of course, with increasing functionality. When I was at my student age, this was our wearable. I had such a Sony Walkman, and that was freedom for us when we were in our 20s. And I guess the 80s really could well be named the Walkman decade. Now, of course, this has been replaced by MP3 players and nowadays by smartphone functionality. But of course, if you look back, this was definitely a wearable. And last but not least, insulin pumps. Now, again, looking at history, this is a wearable, but it's bulky, isn't it? In 1963, they already thought about a wearable insulin pump for diabetics. Now, that was this technology. This is a Beetle, my first car that runs, but I think nowadays we can do better. In the 90s, they were already at the size and the shape that we still have. This is about 111 grams. Nowadays, the pumps are about 80 grams and really nicely wearable. And this is definitely an actuator, even though internally it has power supply, no doubt. Most of them have now radio communication and internal sensors, but all in all, the dominating function is actuation, isn't it? Power supply is an issue, and charging batteries is important. We can have that nicely with a docking station or mobile. But also the body as an energy source should not be forgotten and has been researched quite often in the past. Was looking at breathing activity, at motion in general, arms, and of course the whole body, and also body heat to be a source of powering wearables attached to the body. So for example, this is Ted Sterner's work from the late 90s. This is an example of the attempt of a company called Infineon, a German company, building thermocouple, thermo elements to really harvest the heat emitted by the body for powering wearables. Electrostatic and piezoelectric converters have also been researched quite strongly. Usually they are below 1 milliwatt, which means that many of the wearables nowadays cannot be so nicely powered. And last but not least, there's also and has been work on flexible solar modules powering wearables. So there are various options to do that. If you look at categories a little bit more in detail, I think we can define and categorize the arena, the scenario of wearables into 3 major groups. Devices that we attach to the body with a closed housing, normally to the wrist, for example. Then we may have things integrated into clothing, and we should also consider implants. So those 3, I think, are nice first level categorization. And let's look a little bit more in detail what can be behind this. I have broad examples. This is a nice one, I thought. It's a little bit exotic and doesn't come to mind all the time, but I enjoyed this quite strongly as early it already encapsulated 3 modes: heat transfer measurements, motion, and bioimpedance to work as a diet assistant. So you were able to also type in what you eat, and the device would tell you if you gain or lose weight. An interesting and actually quite important application. Benny is in the audience, so hello, and this is of course your work. Just briefly, there have been early sensors. This was one of the earliest, I think, for motion monitoring with a device behind the ear, attached to the body behind the ear, which is a good location as the physiological sensing for motion, for orientation in space is located in close neighborhood, isn't it? Smart watches are around, and nowadays they measure lots of things: acceleration, barometric pressure, environmental light, optical PPG and DCG, and some of which we will cover a little bit more in detail. So this is of course also an encapsulated wearable device attached to the body from outside. Now, what about textiles? Textiles is a little different. Textiles have the advantage of being close to the body, very close actually, as if you think of underwear especially. And we always wear them, and they are accompanying our day-to-day life. So it is very natural to think of them as becoming a wearable electronic device, but it means that electronics have to meet fibers. Here also we can have different categorizations, different levels of integration, one being textile carriers. Then that means electronic embedded into textiles. We can also think of partially integrated textile structures, like t-shirts, where the electrodes and some conductors are woven into the fabric, but there is also rigid electronics somehow connected to this. We can think of fully integrated structures like the smart shirt, and textile electronics on yarn level. That is still, I guess, future and science fiction at the moment, but have been thought about at least. Now for category 1, there are examples like bras connecting a polar belt, or these under the pants, the underwear that was developed by Philips together with the textile manufacturer encapsulating electronics for ECG measurement, or others, jackets carrying devices and connecting by cables, and so on. Category 2, as I said, goes a little further by having integration of at least conductors and electrodes. Here are examples from various projects. Electrodes means that you have to have conductive covering somehow, either by silver-coated polyamide, as we have done in several of our projects, or by foam-based electrodes, or more recently these PDOT PSS-based electrodes, which are flexible and nicely conducting. In the middle, you see a project that we have done together with Philips and Clothing Plus to integrate impulse cardiography into a textile carrier, but of course only partially embedded, the electrodes and the textile, and especially the wires, but there is also a wearable device in the cardiography measurement. And here we have an example of a multi-channel ECG measurement embedded into textiles. There are commercial examples for this, for example, from sport activity, various kinds, as already mentioned. And then there is ECG shirts in various types since at least 15 years. From our own experience, I may point your attention to a project that we call the Aachen Thirst Sensor, where we actually focused on impedance measurement, classically for assessing the fluid balance in the body. This is done hand to foot or knee to arm. And this we implemented into such a body. Now, not everybody wears a body, even though we do have incontinent patients doing so at adult age. But nevertheless, it would be better to have something that fits everybody. So we actually showed that it is possible to measure for channel bioimpedance signals from knee to knee and put everything in one pant and an electronic carrier at the belt stage. The thirst sensor was meant to measure water content in the body and targeting people who did not drink enough, getting dry, especially aged people. And we were testing this in elderly homes in the neighborhood of Aachen. But unfortunately, ethics committee did not allow us to do a trial on this because depriving people of drinking is quite dangerous. So we then continued with overhydrated patients in dialysis where it worked quite nicely. But then it was not wearable anymore. Okay, but that's life and that's research. Active implants. Also, we have various types. Prominent, for example, are heart pacemakers and ICDs, implantable defibrillators, which come with their own radio, typically in the 402 to 405 megahertz band, ISM band, with a communication service called MIX, allowing to communicate with the implant from outside, from a base station on your drawer, for example, overnight. And also there are cardiac event recorders that people use whenever you're not or you're not diagnosed properly with a Holter ECG of 24 hours. Rare events, for example, benefit from such implanted device that also have a communication link attached to this, and definitely is a wearable. Cochlear implants also are very wearable, I think. So this is, in the old days, has been a speech processor outside together with a microphone communicating with some implanted part that was powered from outside and then going to the cochlea and stimulating the nerves and the sensors inside the cochlea. Nowadays, this is all embedded into a behind the ear unit quite nicely, microphone and power, speech processing and battery. And that is even comes with a special purpose, Bluetooth to save power, of course. Another example is an implanted brain pressure sensor, intracranial pressure sensor, which communicates with RFID technology by inductive coupling, 13.56 megahertz in this case, and then is interrogated from outside to get information on the patient's brain pressure. And I was lucky to be on the team testing these devices for long-term endurance in animal trials. Now, applications. Of course, motion is an example, is a large example, physical activity, and there are various applications for this. Sports, of course, but also motion labs, and there are various devices, and I don't think this talk will cover this in detail, but fitness trackers and also smartwatches can be used. But there are more exotic or more medical applications, for example, in the sleep lab, where you want to have dedicated measurements. An example some years ago has been the ActiWatch, measuring activity of your legs. There are diseases attached to sleep disturbances like restless leg syndrome, for example, where you want to quantify the motion of the legs during sleep. And of course, tremor, this is ongoing research in our case, and I guess many others are doing this also. This was one of our early devices to actually catch the amount of tremor in a patient. Orthopedics and motion lab in general benefits also from wearables like soles, intelligent soles in shoe inlets. And pressure distribution, for example, is quite important information for that. ECG, we have already talked about briefly. Application scenarios include exercise, but there have also been one-channel ECGs on a little more mature level, on a more diagnostic level, and also multi-channel ECG systems, which come with placement of electrodes to allow amateurs to also position electrodes properly for multi-channel home measurements, and this case, the cardioscout was then transmitting information to a base station from a moving patient that has the electrode placed properly. There are more placement scenarios like this silicon belt or half belt, allowing to connect properly and measure 12-channel ECG properly. You can also do ECG with smart watches these days, as I'm sure you have seen. There have been nice large trials recently on atrial fibrillation. I will come back to this, but this is old technology actually, or old application. There has been one device capable of doing that in 2007 already. I guess this is quite some time ago, even though of course this was not with a color screen and not as advanced. This was capable of doing ECG already in a similar way as nowadays. This is recently, and I will come back to this, 400,000 Apple Watch carriers and users have contributed to data that was analyzed for heart rhythm problems, and smartwatch was found to allow early detection of atrial fibrillation quite nicely. Let's look at PPG. Now, this is another wearable device that I guess most of us either have or have at least seen often. This is a finger device, but early, this was already investigated for positioning such devices in different locations, like behind the ear. Of course, this is integrated into watches nowadays, and also as a ring. Now, look at the date. This is 2003, almost 20 years ago. That was, I think, one of the first rings for PPG measurements that I'm aware of, but it was quite bulky. 20 years later, however, this is very, very smooth and even fashionable, I think, measuring heart rate, respiratory rate, temperature, and movement. So quite some functionality in such a small device, only 4 to 6 grams. So I think that's quite an integration level that has recently been launched. In my chair, we have started with these investigations very early, and we looked at devices that you can not put behind, but in the ear channel, with the idea that in the ear is protected against light pollution and also against too much motion artifacts, and very close to the location of the inner ear. And we wanted to know if we can not just do PPG, but also saturation measurements here. Now, of course, in the beginning, these eyes were shining very red. That was too much energy waste and not very fashionable either. So this was reduced, as you see, is myself carrying the first prototype. This was developed together with SIS, Institute for Microsensors, and their sensors were actually placed in an ear mold that was manufactured by Audia Technics. And then we did the electronics for this, and we had individually customized and universal elastic ear molds. This was tested for desaturation studies, human hypoxia studies, actually, in Lübeck with 10 healthy volunteers, where we really got them to 70% of oxygen, arterial oxygen saturation. This you cannot do outside a clinical environment, so they have to be taken care of very carefully and also examined before for cardiac health. But if you do this, then you can bring these people virtually to Mount Everest, and it worked very well. We would have passed an FDA approval procedure with this device, actually. So we would have been accurate enough. We then started to put the electronics behind the ear as well to create in behind the ear unit very light, and batteries 60 milliamps. That may have been a little low with energy supply. So we got 15 grams without housing, but only 90 minutes of operation. But there's a lot of room to improve this further. So this was a demonstration, which I think is not too bad. We should not forget glucose. This is also a wearable, and this has been around since 2005. This is from 2015. with a test of several vendors in parallel. Nowadays, these devices are very small and attached to smartphones, very wearable, keeping people mobile, and they serve as early warning and tendency monitors to get a better feeling of your metabolism in this disease. Now, of course, we can also think of connectors with a pump and then come up with a closed loop system. And indeed, after FDA approval in 2016, this is now around. By now we have 3, that's wrong, actually 4 that just recently launched a 4th device allowing to close the loop with glucose sensors, interstitial glucose sensors and pumps. So nice research, nice work. And there is a lot of research going on also for control here. Now, beyond individual wearables, most of these devices that we have discussed so far are individual wearables. And whenever we benefit from spatial location changes and arranging things at different locations, then the question of communication between sensor nodes come into the game, and then we are in the area of body sensor networks or body area networks or wireless sensor networks or whatever you call this. This is also an area which has been launched maybe 20 years ago, less than 20, 2003 what these papers were, and the conferences also started around 2004, bringing together the community in this area. These sensors are in different locations: movement, ECG, EEG, GSR, and so on, SpO2, and whatever you can think of. Now, there is communication between the sensors in such a case. Obviously, that can be either Zigbee or Bluetooth. Nowadays, low energy especially. And in our case, we use the ISM band for proprietary communication, because this is very energy efficient. So there are various opportunities. Then there normally is a central node communicating with the world outside, often in a star topology or in some other hierarchical topologies, which are also extended star can also be used. There are several examples for dedicated applications, for example, motion tracking and orientation in space. This is a motion sensor at 11 grams, 11.2, with a very low latency for communication between sensors, which is quite important if you do distributed motion tracking, I think. So Xsense is an example. This is an old version from 2005. This is from now, much smaller and much nicer. Shimmer, of course, has sensors that you may also want to consider whenever you need a device like this. These devices come with various sensors: ECG, EMG, respiration, and 9 degrees of freedom. Then there is a mobile guide analysis, for example, as another example. So there are various vendors that you should look for proper companies doing this. This one is dedicated for motion analysis and connection to gate labs. And there is another one that we operate in our own gate lab, which comes with motion and EMG sensors to quantify dedicated muscles and motions. Now, we operate our own network as a research platform, because this is free and open to us, and we can modify and add new sensors on demand. We are able to do PPG and EMG and ECG, but also impedance measurements for muscle analysis at the moment, and all kinds of motion signals. And this is nicely synchronized and also wireless. The first version was in the ISM band at 433, and this is a little video showing this. Called this Ipanema. And this comes, in this case, with 3 sensors for this little demonstration. And all the signals are streamed to a tablet that is then coming synchronized and can be stored or for analysis or whatever. The new version now comes with a Cortex and has 12 hours at 230 milliamps of battery with 30 grams per node. So maybe this is also for those of you who are new in the area, a good, this is reachable with university level research, I think, and is also open for sharing if somebody has interest. We are actually doing this in a Parkinson trial at the moment with 3 sensors attached to the patients. We have also used this to quantify skiing. So this is myself going downhill, and you can see this, the height going downhill and also all the motions. I'm not a good skier, as you obviously see, but it's, I think, nevertheless illustrative to see even these small change of height we could diagnose nicely. Last but not least, Geronto technology is an application for such devices where we have a nice gate lab for old studies and trials with old patients. And here we are active in developing exoskeletons for support of patients, which is currently equipped with this body sensor networks to capture the motion of the rest of the body. So this, I think, is also a good application area for a body sensor network. Right. So this is a mature area, I think. Body sensor networks have started 15 to 20 years ago. There's literature, there are conferences, and there are textbooks. And here I'm also giving you a few of the recent textbooks, or some of them are already a few years in the market. Guangzong's book, for example, but also Edwards' recent book on wearable sensors are an opportunity to study deeper. Large players are in the market, of course, but these data biotopes are typically closed, which I think is a little problem and maybe a discussion, worth a discussion. There are body sensor network conferences, which you may want to look at. We had the pleasure to host this in 2007 and in 2017. It was started actually at Imperial College in 2004. So I think Benny can comment on this. So then there is another one, body area networks, similar topics. Look out for electronic tattoos. They may be on the verge of coming. Let's see if this makes it. Flexible electronics, it can be a wearable. AI will be connected, and I think this is also for discussion, something. AI will meet and is meeting wearables. So how do we do this in the research arena properly? Because lots of the data that is collected at the moment, and I've mentioned this trial with the data collected with the smartwatches, is not available to be shared. This is private property. And I think we should, in the area of wearables, in the research community, do an effort for academic research and data sharing. So maybe this is also something you want to comment on. Thank you very much for listening.
Thank you very much for the interesting talk, I would say. I see already a questions, but in the meanwhile, also encourage the audience to use the Q&A tool for further questions. So the first question from the audience is regarding the effects, the adverse effects of the radiations, basically. Transmission of data via sensors or the mere attachment of some sensors to the human body bring about emissions of radiations. We know that radiation might be, detrimental for the human tissues. So the question is about basically how do we handle the effect and the impact of radiations.
So this is of course an important question, but in general, at least in our body sensor networks, we are far below the allowed emission standards. that was the question of harming the body or interfering with the body physiological function. I think if you use your cell phone regularly, you're doing more harm. There's another question attached to this, and that actually is one of the explanations why we use the ISM band, and that is shading. With 2.4 gigahertz, you get more shading by the body than with 433 megahertz, for example, or 800 megahertz. So communication around the body and through the body is easier in that. That was actually why we picked that, or one of the reasons.
Yes, thank you for the question. If there are no other questions, still we got some minutes before the we are behind the schedule, so ahead of schedule actually. So maybe if there are no questions, I have a couple of questions for you. First of all, I was wondering the possible impact in the near future of the integration between 5G, but also beyond technologies with wearable computing systems, particularly probably with the wearables that have highly hardware constraints in terms of processing, for example, capabilities. So I was wondering whether you see a positive but significant impact of 5G integration with wearable computing systems.
So in the end, this is always a question of power density. How much wearable power battery storage do you have around you? What are the use cases with rechargement and with availability of the functionality independent of the charging status? Right? I mean, it's very bad if you get a heart attack and your monitor is just not working properly that day because you have forgotten to charge it properly. So how do you do this? Now, of course, 5G will be ubiquitous and even 6G especially. So let's see, but 5G is meant to power communication very frequently and make cars and everything interacting very fast. If we talk about wearables, we have to also talk about energy consumption. In our body sensor networks, just to give an example, a quarter of the power supply is for communication. Now, we may want to invest into this. I know that you can do the Bluetooth stack better, and then a commercial one that we integrated here. So such things are coming. If this is not eating up too much energy for communication and for processing, then we can fuse these things also in a wearable device. Other than that, of course, you can always think of having a 5G device as a master node communicating with the world and locally low power devices around you. I think Benny is putting
it.
Yeah,
definitely makes sense, yes. Thank you. I see Professor Law raised his hand, so you might make a question yourself.
Hi, Stefan. Good to see you. I have a completely different questions because probably we all know there's a global shortage of electronic components. And I mean, we are having troubles sourcing a lot of components. And Stefan, do you have a view on this or any insight from Philips that would there be a better supply next year?
So I guess that is worth $1 million, such an answer, isn't it? I don't know. Now, I have no idea. This is a problem. I think it shows us how vulnerable worldwide trading can be, I think. And we have to take measures against such shortages in the long run. We have to have more distributed production, more distributed engineering work, and not just say, well, this group or this country or this area of the world is doing this and the other is doing this, and we ship our things around all the time. because this may not be the proper solution for the future, I think.
Yeah, I think we're running short of time, so thanks, Devin.
Sure.
Okay, let's thank the speaker once more, and we have to move to the second speaker this session. So let me share my screen to introduce it. Okay, so it's a very pleasure to introduce Professor Dae-Jong Kim from Seoul National University. He will give us a talk titled Wearable Bioelectronics Using Intrinsically Soft Electronic Materials. But let me spend a couple of words for Professor Kim as well. So he's a chemical engineering from Seoul National University in Korea. And he's also received a PhD degree in material science and engineering from University of Illinois at Urbana-Champaign in 2009. From 2009 to 2011, he was also a postdoc at the same university. He also joined Seoul National University in 2011 and is currently serving as professor in School of Chemical and Biological Engineering at this university. His research interests include nanomaterials and deformable devices and their application to biointegrated and bioinspired electronics. Among his many awards, for sure, it's definitely worth to note that he has been nominated highly cited researcher by Clarivate 3 years in a row, from 2018 to 2020. So I would like to pass the floor to Professor Kim. Yes, the floor is yours.
Thank you. May I share my screen now?
Absolutely, yes. Okay, I can see your slides, perfect.
Thank you for a nice introduction and also kind invitation. I belong to chemical engineering department, so I usually work on the materials, and through the material innovation, we want to develop a new type of devices, which can be either wearable devices and implantable devices. And today, I will focus on intrinsically soft electronic materials for skin mountable bioelectronics. This schematic illustration shows our group's overall research on bioelectronics. We have been working on the nanomaterials-based soft bioelectronics. Soft bioelectronics includes flexible and stretchable bioelectronics, and we usually use nanomaterials. So our research usually starts from the synthesis of nanomaterials and develop a new type of soft electronic materials and apply that to the soft bioelectronic devices. And such soft bioelectronic devices include implantable devices for example, ECG measurement, EEG measurement, brain tumor treatment, prosthetic eye, endovascular devices, and also wearable devices for various kinds of vital sign monitoring, real-time display, drug delivery, and so on. And today, since the workshop is about the wearable devices, I'll focus on the wearable devices. And at first, I will talk about how to make flexible, stretchable, and wearable devices, and then we'll move on to the materials and how we can make innovations in wearable devices through the new material development. First, why do we need nanomaterials? If you take a look at this graph, if we decrease the thickness 10 to the 4 times, then the flexural rigidity of the target material can be decreased 18 times. Dramatic decrease of the rigidity. That means by using this principle, we can make silicon wafer, rigid and brittle silicon wafer, to be very, very flexible by simply decreasing the thickness down to several hundreds nanometers. That's the reason why we are using nanomaterials to make the bulk state high quality material to be flexible. So by using this kind of flexible nano materials, in this case, single crystal silicon nanomembrane, we can fabricate flexible devices. In this particular case, we transfer printed doped silicon on the Kapton film from DuPont. The thickness is 25 micron, and then deposited dielectric material and metal to make NMOS, PMOS, and CMOS, and ring oscillators. While it is flexible, the performance of the device is comparable to the devices fabricated on the conventional silicon wafer. Also, we can develop this flexible system into foldable system. We typically use 2 kinds of strategies. The first one is to decrease the thickness, ultra-thin type device. And the second strategy is to use neutral mechanical plane, or mechanics-based strategy. These show the cross-sectional illustration of the flexible device and ultra-thin device. This device corresponds to the previous one, this one. So as I explained in the previous slide, we used commercial plastic substrate, Kapton film, whose typical thickness is between 25 micron to 100 micron, and we transfer printed single crystal silicon and deposited SiO2 metal. The entire device thickness was less than 1 micron, and in comparison with the plastic substrate thickness, this is much, much thinner. And if we bend this system, then the strain will be induced on the device, and the equation is like this. As we decrease the bending radius, that means as we bend the system much, the strain will be increased. And if the strain on the device is higher than 1%, then we will see mechanical fractures and cracks on the device. To minimize the induced strain, what we can do is to minimize the thickness. So we can use the ultra-thin substrate. Instead of using commercial substrate, we can spin coat polyimide, for example. Then the spin-coated polyimide typically has the thickness of 1 micron. So in comparison with 100 micron commercial plastic substrate, the thickness can be decreased 100 times. That means the induced strain can be decreased 100 times. Also, on the device, we can spin coat another layer of 1 micron polyimide. In that case, if we bend the device, then at the top surface, tensile strain will be induced. At the bottom surface, compressive strain will be induced. But at the center, the tensile strain and the compressive strain will be compensating each other. And if we can locate our device at that specific position, which is called as neutral mechanical plane, then the induced strain due to the bending can be minimized, almost ignorable, negligible. So by using these 2 strategies, ultra-thin device and neutral mechanical plane design, we can fold the CMOS inverter around 100 micron thick cover glass. Actually, this these two strategies are being used in display industry, foldable, to fabricate the foldable LEDs, OLEDs. And we can develop this foldable system into a stretchable system by simply changing the straight interconnection into this kind of serpentine interconnection. Still, the device thickness is very thin, and we use the neutral mechanical design, but the change is the design of the interconnection. By using the serpentine types interconnection, we can stretch the device up to 50%, 100%. And by using this stretchable device design strategy, we developed the skin mount of electronics in 2011. In this case, we used gallium arsenide nanomembrane, silicon nanomembrane, conductive rubber, and metal films to make various kinds of sensors, LEDs, and we also have antenna. And the entire thickness is around the 3 micron, and we use serpentine design, so the system is stretchable. Therefore, the device can be conformably laminated on the human skin. And on the human skin, we could measure temperature, electrophysiological signal, and so on. But after this work, 2011, many advanced types of skin mountable devices have been reported from the academia and also from industry. For example, in 2014, from Raj's group, an interesting wearable device was reported. In this case, chips, but small chips, small size chips, were interconnected with the serpentine stretchable electrodes interconnections, and through the serpentine stretchable antenna, the electrophysiological signals such as electrocardiogram or myogram could be transmitted to the device. And still, this device is quite soft and stretchable, so it could maintain a very good conformal contact on the human skin. So the contact impedance could be minimized, and the signal-to-noise ratio can be increased. In this case, ultra-thin electrode was used for pressure sensor and strain gauge, so the skin deformation could be monitored in real time. A similar device could be fabricated with the polymer, or in this case, LEDs, LED arrays were connected with a optical biosensor to display the measurement signal in real time, which was developed by Samsung. So there are various kinds of wearable bioelectronic, skin mountable bioelectronic devices, and the key component, as you may see, is the stretchable electrode. The largest part of the device consists of stretchable electrodes, and therefore the mechanical property of the stretchable device, such as stretchability and softness, is highly important to make a very good interface between the biosensor and the skin, human skin. So maximize the sensing quality and minimize the noise level. And also these stretchable electrodes could be used for not just interconnection, but also for mechanical sensors or wireless power transmission or wireless data transmission. So the performance of the stretchable electrodes can determine the performance of the entire system. Therefore, high performance, in other words, high mechanical and high electrical performance of stretchable electrode is very important. So there have been many reports from the academia, usually, and recently, the rigid Berkey electrodes could be replaced with the stretchable electrodes, as I briefly introduced in the previous slide. But still, there are remaining challenges, especially local mechanical mismatch between the electrode, stretchable electrode, and the human skin. The modulus means the material property, which can represent the stiffness of the material. And typical conducting polymer or polyimide modulus is in the range of gigapascal, and metal is even stiffer. And such gigapascal range modulus can be found in our body at the bone. So in comparison with other soft tissues, as cardiac muscle, or brain tissue, or dermis, this stiffness of polyimide or conducting polymer metal too stiff. So there is a huge gap in terms of the modulus or stiffness between the human tissue, even for the dermis, skin tissue. The mechanical modulus is in the megapascal range, but the material is gigapascal range. Therefore, there should be continuous stress on the interface between the electrode, stretchable electrode, and the human skin. And such continuous induced strain can cause skin irritation. Also, such stress can be applied to the electrode, and fatigue will be accumulated. Therefore, the deposited metal film can be cracked. So the entire antenna or entire connection may not work. In addition, in the case of a skin mount of device, since the skin has various kinds of voids due to its tough morphology, so even after we make a good contact using the devices shown in the previous slide, still there are micro scale air gaps between the electrode and the human skin. So because of these air gaps, impedance can be increased, which can cause lower signal-to-noise ratio in comparison with perfectly contact device electrode. So previously, people have used rigid materials with smart designs, serpentine designs, for example, to make a stretchable platform and induce the contact between the device and the human skin. But from several years ago, there has been efforts to develop intrinsically soft conductive materials. For example, hydrogel is extremely soft material, so it can make a very good contact on the human skin without any air gap or no voice, as shown in this SEM image. And we can include conductive nanomaterials or polymeric materials with this hydrogel. For example, we can include PSS to make a conductive hydrogel, or we can include nanoparticles, metal nanoparticles, or even metal nanowires can be included in the hydrogel matrix. Then we can confer conductivity on the hydrogel, and this hydrogel can be very practical and also high performance interfacial material between the human skin and the device. So we use such soft hydrogel, conductive hydrogel, but a very thin form. Typically, the thickness is 100 micron or less, to make the good interface between the flexible device and the human skin. So using this one, we could measure TCPO2. We could do the transdermal drug delivery, impedance sensing, and electrical stimulation. And due to the softness of the conductive hydrogel, a very good contact could be made. So biosensing or stimulation performance would be maximum. Although the conductive hydrogel can make very good contact because of its extremely high softness, the disadvantage of the hydrogel-based composite is in its electrical performance. although the mechanical stiffness and mechanical softness and stretchability are very, very high, the electrical conductivity is much lower than metal. Typically, metal has the conductivity of 100,000 Siemens per centimeter, but conductive hydrogens typically show the conductivity less than 100 Siemens per centimeter. So instead of using hydrogel, there is another approach to use elastomer-based composites to maximize the electrical performance. Actually, that is very important for interconnection and the antenna applications, because in such cases, high conductivity, in other words, very low resistance, is very important. So typically, thermoplastic elastomers have been used, and for conductive fillers, metal nanowires, especially silver nanowires, have been used. So our group also has been working on that stretchable nanocomposites. As I mentioned, we have used ultra-long silver nanowires. The reason why we chose ultra-long silver nanowires is because silver has the highest conductivity among all metal, and also long nanowires can be easily connected to each other. So inside the polymer, inside the rubber elastomer, these metal nanowires can be connected to each other to make a percolation network and conductive pathway. Early in 2015, we could achieve 77,000 Siemens per centimeter electrical performance and mechanical performance, the stretchability of 50%. This may not be bad, but still a long way to go to catch metal conductivity. Although metal is not stretchable, and this material is stretchable, still the electrical performance shows a huge gap. So we wanted to improve the conductivity, and the easiest way to increase the conductivity in this conductive nanocomposite is to add more nanowires. Into the rubber, we can add more and more nanowires, then more metal will lead to higher conductivity. But at the same time, as we increase the concentration of the silver nanowire, the mechanical softness of the composite will be decreased. So the composite will lose the original rubbery property, rather it will become stiff. So there is a trade-off between the conductivity and the softness, although we have to improve both, which is quite challenging. Another problem is in silver nanowire. Silver can be easily oxidized, and if the nanowire surface is oxidized, then contact resistance between nanowires will decrease. So eventually, the conductivity will be decreased. Also, silver nanowires, especially in its nanoscale dimension, nanowires can be easily dissolved in biofluids, and the wearable devices are always, especially skin-mounted wearable devices, are always exposed to human sweat, which can dissolve silver nanowires, and silver ions can be leached out, which is toxic. So there is a biocompatibility issue which we have to solve to commercialize this material. To solve such issues, we changed the material from silver nanowire to core shell type nanowire. So the core is still silver because the silver has the highest conductivity among all metal, but the shell, we added a thick shell of gold, and gold is inert material, so it is not oxidized and it is biocompatible. So we can solve the biocompatibility issue and also oxidation issue. And usually we mix these nanowires with the rubber, such as SCBS rubber. And if we evaporate the solvent, then we will be able to obtain the solid state conductive rubber. But in this case, we optimized the curing temperature and added some additives, so we could induce microscale phase separation of the rubber phase from the nanowire phase. Therefore, we could maximize the stretchability. In comparison with the previous case, the stretchability was 50% and the conductivity was 7,000. But now the stretchability could be improved to 840% and conductivity 32,000 joules per centimeter. The material is highly conductive and also stretchable. And using this conductive rubber, we fabricated skin mountable devices. We use the molding process. Since rubber cannot, we couldn't apply the photoretrography to the rubber. We typically use molding process or screen printing to make this kind of device. So since we use this molding or printing process, the typical thickness of the interconnection, the width is around 100 micron. The thickness of the device is around 20 micron or 10 micron. But since the material is intrinsically soft, it could make very good contact on the human skin. And due to the contact, the impedance could be lowered a lot. So ECG or EMG could be measured, and we could apply electrical stimulation to the skin. And also we could use a heater to apply heat to the joint region and for the purpose of thermotherapy. So various kinds of sensing or stimulations could be achieved using this material. But still a way to go. Our goal, the extremely high performance intrinsically stretchable electrode, may be located here in this chart. Y-axis is stretchability, the x-axis is conductivity, and as I mentioned, typically metal has the conductivity higher than 100,000 centimeters, so our goal should be higher than this one. And the maximum stretchability reported in the academia was 1,000%, so we want to achieve 1,000% stretchability. In addition, we want ultra thin thickness. If we want to make integrated device, multi-layered integrated device, and if we use a rubber introduced in the previous slide whose thickness is 20 micron, and if we have 10 layers, then the thickness can be very thick, several hundred micron. So to make an integrated device, we need a much thinner conductor. Hopefully, the thickness less than 1 micron in several hundred nanometer range. Also, we need to be able to apply the high resolution patterning, hopefully photoretrography, but in the case of rubber, since the nanowire is mixed in the rubber, we cannot apply UV and development process for the retrography, so we typically use the mold or screen printing. Therefore, a new material is needed to increase the patterning resolution to be comparable with the conventional electronic material. So achieving these four goals, requirements simultaneously is highly challenging. Therefore, it is necessary to develop a new material. So we developed a novel float assembly method, and using this method, this is quite similar with the Langmuir-Blasi method, assembly method, and using this method, we could develop a nanomembrane that satisfies all such requirements. High stretchability, 1,000%, high conductivity, higher than 100,000 centimeter, the thickness of 250 nanometer, and pattern resolution of 20 micron. The fabrication process is quite simple. We can first prepare a solution of the silver nanowire mixed with rubber, SEBS rubber, and solvent toluene, and a little bit of ethanol. And we can drop these solution on the water, inside the water container. Then the material will float because SEBS and toluene is oily phase. Pitch is not mixed with the water, so they will float on water. And if we apply surfactant, because surfactant wants to occupy the water surface, that it will push the rubber and nanowire to the edge of the container. And after that, we can wait a few minutes, then solvent will be evaporated. So we will be able to obtain a very thin, highly stretchable, highly conductive nanomembrane on water. And the thickness of the nanomembrane is 215 nanometer, and nanowires are assembled between the rubber and water. So nanowires are aligned and compactly packed and embedded in the SCBS rubber. I will explain more detailed structure following. And this movie shows the solution injection process. Quite easy. We can just drop the solution, then the SCBS rubber and the pen will be floating on water, and nanowires will be located at the interface between rubber and water. And after that, we can drop a few drops of surfactants. Then surfactant wants to occupy the water surface, so they push the nanowire to the edge. And also, SCBS will be pushed, so the nanowires can be compactly assembled. And if the solvent evaporates, then we can obtain a nanomembrane. So this material has a very unique structure, like gum and teeth structure. This is cross-sectional illustration in the TM image. So nanowire partially embedded in the SCBS rubber. The thickness is 110 and 140, so in total 250. And if we see the top view, then the nanowires are compactly assembled. And because of this structure, unique structure, we could achieve 250 nanometer thickness, high stretchability, resolution, patterning, and let's explain one by one. So this shows the stretchability. The rubber is quite elastic, but even when we stretch the rubber 500%, nanowires are connected to each other. So electron can pass through this percolation network, so still the membrane can be conductive. This movie shows the stretching demonstration. We can stretch the nanomembrane up to 1000% repeatedly. And due to the unique structure, partially embedded structure, we can apply now photolithography. We want to pattern nanowires, and nanowires are partially exposed. The previous case, when we simply mix the nanowires with rubber, nanowires are embedded inside rubber, so we could not achieve the wet etching. But in this case, after partially protecting the nanowires with photoresist, we can apply a wet etchant to the nanowire, in this case silver etchant. Then and then we can remove photoresist to make a nanowire pattern. This is 20 micron NS-based pattern, and other patterns can be fabricated, and all these patterns are intrinsically stretchable. To maximize the conductivity, we used cold welding. As a synthesized nanowires have PVP ligands, which prevent the intimate contact between nanowires. But if we apply sodium chloride solution, then sodium chloride will remove polyvinyl peroxide, and when the water evaporates, the nanowires will experience high capillary force. So low temperature welding can be made, and after welding, the conductivity of the nanomembrane can be increased higher than 10 to the 5, 100,000 Siemens per cent. We can go further. We can stack two nanomembranes, but there are two methods: aligned stacking or perpendicular stacking. If we align nanowires top and bottom and stack these two layers together, then through this nanowire direction, if we measure the conductivity following the nanowire direction, then the conductivity is up to 150 Siemens per second, 150,000 Siemens per second. Though to the vertical direction, the is only 50,000 centimeters is still high, but lower than this value. So there is an anisotropy. But if we use the perpendicular stacking, the top is horizontal direction, the bottom is the vertical direction, then we can remove that anisotropy. So regardless of the direction, the conductivity higher than 100,000% can be achieved, while the stretchability could be 1,000%. So now using this material, ultra-thin, highly stretchable, highly conductive nanomembrane, we achieve these four goals. Metal-like conductivity higher than 100,000 centimeter, very thin thickness, 250 nanometer in the case of stacked material, 500 nanometer, stretchability of 1,000%. So this may be a very proper material for skin mountable bioelectronics. And based on this material, we fabricated multifunctional skin-like electronics. It's like a second skin. It can make very good conformable human skin. So if we take a look at the interface between the sensor and the skin replica, there is no air voids. So very good conformable contact can be made. It's almost similar with the hydrogel case, although the stretchability and the conductivity is much, much higher than hydrogel, and the thickness is much thinner than the hydrogel. Since the thickness is very thin, and since we can apply photolithography, so we could make various kinds of sensors, interconnections, via layers, and also we can use different types of nanomaterials, gold nanoparticle, silver nanoparticle, silver nanowire, or coaxial type nanowires, and we can stack these layers all together to make an integrated device. If we use conventional rubber, the one layer thickness would be 20 micron. That means the entire thickness would be very thick. In that case, the thickness, we cannot make this contact. The rubber will be just detached out from the skin when we deform the skin. This slide shows the characterization results of each sensor: electrophysiological sensor, temperature sensor, strain sensor, and the humidity sensor. And by integrating these sensors, we could measure ECG or EMG, and also we could measure strain to monitor the human body motion. We could check the temperature, so infection may be detected using temperature monitoring. Skin humidity can be monitored, so this can be used for determining the skin health, which is used for cosmetics. Anyway, with simple device, just second skin-like device, we could measure various kinds of factors, biological factors, as an array. So we have several sensors on one layer, so we have arrays of different integrated. That's it. So our group is working on nanomaterials-based software electronics to solve unmet clinical challenges. And today, I focus on materials and the sensors and interconnection and antenna, things like that. But we are also working on various kinds of device components, foldable QLED, wearable QLED, wirelessly integrated body network, implantable device, glioblastoma treatment, heart failure treatment, in vitro type, circuit, etc. So if you are interested in these bioelectronic devices, please visit our website and you'll be able to find the publication. Thank you for your attention.
Thank you, Professor Kim, for your very interesting and exhaustive talk. Very, very interesting. I already see a couple of questions from the audience, so I'm gonna quick reading them. So the first question is about the interface between soft and hard electronics. How difficult is interfacing these two layers? Do you have any suggestions about this?
How difficult is to make the interface between the soft material and the skin?
Yes.
It depends on the thickness of the soft material and the modulus material. Of course, if the modulus of the material is too stiff, in other words, if there is a mechanical mismatch between the material and the skin, then conformal contact on the curvilinear human skin would be extremely difficult. That's the reason why we want to match the material modulus to the skin. Typically 1 micron or 1 megapascal or 2 megapascal modulus is good enough. So to match the modulus, we use very soft materials such as Ecoplex or hopefully hydrogel, but in such cases, incorporating high amount of conductive fillers is quite difficult. In the case of hydrogel, the gelation cannot be proceeded if we add too much nanowire. Likewise, PDMS or Ecoplex will not be solidified if we add too much nanowires. Therefore, the electrical performance is quite low. And in such cases, although we can make conformal contact, the local impedance and the resistance may be too high. So in terms of the modulus, such pros and cons exist. Another important thing is the thickness. Although we use a little bit stiff material, if we can decrease the thickness down to hundreds of nanometer, or at least less than 1 micron, then very good conformal contact can be made. But typically, it is very difficult to handle such ultra-thin device. So if we use brittle material and make that material very, very thin, then mechanical crack can be easily formed when we deform the human skin. So that's the reason why we want to stick with soft and elastic materials while we decrease the thickness to make very good contact as well as to obtain the high robustness and reliability of the device on the human skin.
Thank you. I think there is a related question somehow. The next question is, in fact, compared to traditional sensors, what is the durability and robustness of skin interfaced sensors? If you have, let's say, any suggestion on how to improve its useful life.
So the main reason why we are going into intrinsically soft materials such as rubbery, elastic materials is because of the material durability. So in terms of material durability, of course, rigid devices may be best, the conventional rigid devices. But there is a key disadvantage of rigid device in terms of the contact between the sensor and the human skin. Electrophysiology, when we want to measure electrophysiology, impedance is important. But if we want to apply the electrical stimulation, high capacitance can be a problem. If we want to use the skin mount device for the transdermal drug delivery, if there is a small air gap, transdermal drug delivery efficiency will decrease a lot. So there is a clear disadvantage of the rigid devices. So we, the first approach was to thin down conventional metal or semiconductor material to be less than 1 micron to make a conformal contact. But in such cases, as I mentioned, when human skin deforms, the device will be deformed at the same time. And if the local induced strain is higher than 1%, then the metal or semiconductor like a silicon can be easily cracked. So although a very small crack is generated, the entire system may not work. So, but if we use elastic, resilient, conductive material, then the reliability and the durability is much better, at least in terms of the mechanical crack or fracture generation. So the reason why we want to achieve 1000% stretchability, although the skin can be stretched only 20%, 30%, is because if the maximum stretchability is 1000%, and if we just stretch the device 50%, 100,000 times, since the maximum stretchability is very high, the accumulated fatigue can be minimized. But if the maximum stretchability is only 50%, and if you apply 50% stretching several times, then the device may be cracked. So elastic, resilient material with high stretchability is very important to obtain high durability material device.
Okay, I think there is time just for another quick questions, and I see a hand raised from Professor Leonard. So I would, of course, leave Professor Leonard to make the questions, and therefore we can conclude this very interesting part of the session. Please, Professor.
So thank you very much. And thank you, Professor Kim. This was very inspiring talk, I must say, very interesting. Now, I've seen in one of your slides, you have a stacked array of electrode barriers, but also in the lowest layer, there was electronics. Now, is this solid state electronics or is it organic electronics? And if it is solid state, how do you make this one as flexible as the upper layers? Do you make it very thin then, or how do you do this?
So multifunctional integrated skin-like electronics was fabricated with entirely intrinsically soft material. So there is no rigid components, but we can include rigid components. And in such cases, we typically use soft layers underneath and add thinned down device or material on the top. So it is quite difficult to use the thick chip because if the chip is too thick, then although we use the soft substrate, still there is a mechanical mismatch between the human skin. So we typically thin down the device. Maybe we can unpack the chip and grind the substrate. So the thickness of the chip can be thinned down tens of microns. And if, as far as we can disassemble the chip, so one integrated chip can be disassembled into small pieces and thinned down and interconnected with the stretchable electrodes. Then still, and at the bottom, we can have electrodes for electrophysical sensing, temperature sensing, humidity sensing, strain sensing, and on top we can add some wireless modules, and that can be connected to stretchable antenna. Then we can utilize the conventional chips as well as the new soft materials to make an integrated system.
Okay, thank you.
Thank you.
Okay, thank you again for your very interesting talk. Before we make the coffee break, we will restart at 6:10 and European time. I would like to say not to leave, because the last talk of today will be held by one of the big names, very well-known researcher in the area of body sensor networks. So make sure not to lose his talk, okay? We will restart in a bit less than 1 hour, so at 6:10 p.m., okay? Thank you, and meet you in a few minutes. And here we are back to the session. Can you hear me, my voice, first of all?
Yes.
Okay. So it's my pleasure to introduce the last talk of this day one. Professor Benny Law, as I told before, is one of the very well-known researchers in the field of wearable computing, body sensor network. He is currently a senior lecturer at the Hamlin Center at the Imperial College London. His research is mainly focused on pervasive sensing, biomedical engineering, microelectronics, surgical vision, and of course, wearable robotics and machine learning for healthcare, well-being, and sports application. He led a number of translational projects on applying sensing technology in clinical applications. Among the many other services, he is also associate editor of the IEEE Journal of Biomedical and Health Informatics, JBHI. Notably, he was past chair of the IEEE EMBS Wearable Biomedical Sensors and Systems Technical Committee, and is also in the steering committee member of the IEEE EMBS Standards Technical Committee. So I would again welcome Professor Law and pass him the floor.
Okay, can I share my screen? Let me share my screen.
Yes, I can stop my sharing.
Sorry, I need to set my right.
There should be a share screen button.
Just 1 second. Yeah. I may have to quit and reopen because there's some new setting. Otherwise, you won't be able to record what's on the screen. Just bear with me 1 minute. This is a laptop, so.
Okay, apparently we temporarily lost Professor Law, but I guess he will join in a few seconds. Let's see.
Can you see my screen? Or?
I can see the screen, yes. I think this is in presenter mode, so basically we see also the next slide. Okay, perfect.
Right. Okay, so well, thanks the organizer for the invitation to give me a chance to talk about our work at Imperial. So today I'm going to talk about enabling technologies for health and well-being. And so let's start with COVID-19. Well, we're still in the COVID-19 pandemic, but it was at first identified, COVID-19 was first identified for more than 2 years ago. And the world has been in the pandemic for almost 2 years. Despite the success of curbing the pandemic with lockdowns and vaccinations, the new variants are still threatening the global health. The ongoing pandemic has caused significant load onto the already overstretching care services, and which has caused major reduction of care services provided to patients. So And as an example, in the US, the visits to emergency services have reduced by 40%. The ambulatory care practices have reduced by 60%. And the urgent referrals from general practitioners to major cancer care centers for suspected cancer has down by 76%. Increasingly, we are relying on the use of telemedicine, where in the Fair Health Review of 2020, insurance claims show that there was a 3,060% increase in telemedicine claims over 2019 claims. The recent advances in wearables and implantable sensor technologies have greatly supported and enabled the developments and delivery of telemedicine. More physiological parameters can be captured from patients in his or her own home at a very low cost. With the internet connections or 5G via the smartphones, continuous patient data can be streamed and uploaded to the healthcare services, and which enables accurate remote diagnosis and therapy assessments. In this talk, I'll talk about 3 of our recent sensing technologies developments with the aim of enabling better quality of care for patients. So, although this is the wearable workshop, wearable technologies and wearable sensor system workshops, but instead of wearable sensors, I would like to start with talk about an ambulatory sensor for respiratory monitoring. As we know that COVID-19 could cause severe acute respiratory syndromes, disturbing the regular breathing and leading to continuous coughing and breathing difficulties. Given the increasing number of infected cases around the world, patients with mild symptoms are advised to stay home and get treatments with the aim of reducing the stress on primary care services. However, the patient's conditions could get worsened very rapidly. Hence, constant monitoring is needed, especially for those high-risk patients groups. There are already many pervasive wearable sensors, respiratory sensors, which can accurately detect respiratory rate. But user compliance is one major problem for wearable sensors. Most of the sensors are chest strap-like sensors, which could cause discomfort after prolonged use. So in this work, we propose an ambulatory sensor which can detect local airflow variations by respiration sensor on desk in the desk working environment. So it enables accurate quantification of coughing and breathing difficulties. So probably most of you know one common approach for detecting coughing and respiratory rate is just the use of inertial measurement unit, IMU. Strapping the IMUs on the chest of the user, you can detect the patterns. So given the high sensor sensitivity, IMU sensors can detect different breathing patterns, such as weak, normal, and rapid breathing and coughing. These are some sample data showing the IMU sensor signals captured during different breathing patterns and coughing. However, apart from user compliances, such wearable IMU sensors can be affected by motions, and the pattern detections could be confused by similar signal patterns induced by normal daily activities. So with the aim of developing a low-cost pervasive sensors for respiratory monitoring, we investigated the use of a barometric sensor for detecting the breathing patterns. So by positioning the biometric sensor on the user's desk, the sensor can clearly capture the different breathing patterns of the user. So as shown on this graph, and this graphs, you can easily distinguish weak, normal, or rapid breathing, or deep breath, or hold the breath, or when the users left the desk. So the advantage of such ambient sensor is that it does not require any user actions or setup, and it can precisely monitor the breathing patterns of the user. However, there's one concern of such ambient sensor, which is the spatial sensitivity of the sensor. So we've done exhaustive experiments to evaluate the spatial sensitivity of the sensor. So basically, how close the sensor has to be near the user in order to get good detection signals. So it was found that the sensors has a range of about 15 centimeters on the XY plane and around 25 to 35 centimeters on the Z plane. So, which means the sensor can be placed up to about 15 centimeters away from the user on a desk. Like most of the wearable sensor signal informatics, we aim to we need to develop low computational power algorithms for such very small sensor. So this is a diagram of the low computational power algorithm designed for filtering the signals and distinguish different breathing patterns from the sensor. So as you can see, it's relatively straightforward with a few filters plus some logics in the algorithm. Although the algorithm is relatively straightforward, the detection rate is really high. So we ran experiments with 10 subjects, and the accuracy of detecting breathing, coughing, and leaving, which means the user was away from the desk, was very high with 97% on average. The algorithm also detects the different respiratory patterns and also coughing, i.e. the 5 different respiration events with an accuracy of nearly 99%. So it shows that the feasibility of such a low-cost sensors with providing continuous monitoring of patients at their own home. So older adults, the high-risk group of people which seriously affected by COVID-19. Given the reduced healthcare services provided during the pandemic, elderly followers are mostly affected, as elderly followers often require long hospital stay and have high risk of fall again. Home care may not be suitable for them, and fall can lead to life-threatening conditions. To address the need for continuous monitoring of elderly followers, we have been working together with NETTEC, the National Electronics and Computer Technology Center of Thailand, in developing a sensing system for fall prevention. It's designed for fall prevention and detections, particularly for hospital and residential care environment where the patients will be wearing the sensor on the abdomen, and if a fall is detected, an alarm will be triggered to warn the nurse and the caretaker that an early interventions can be introduced. So it's is designed and based on a miniaturized sensor attached to the abdomen. It has with a built-in on-node processing algorithm. The IMU-based wearable sensor can capture precursors of falls and detect falls to provide warnings for early interventions. At the moment, we have run a couple of pilot studies in Thailand, and our studies have been disrupted by the COVID-19. But we soon resume our study in a few hospitals and also residential care home in Thailand. So this shows some screenshot of the apps developed for the caretaker and also the SIM administrators. So one of the major challenges in fall detection is detecting slow fall. So most of the fall detection algorithms are designed for trip fall or sudden falls. However, most of them cannot detect such slow fall. So older adults often suffer from slow fall, where the elderly fall slowly onto the ground due to muscle weakness. For example, many falls happens when the older adults were trying to sit down or get up from a chair. They often fall very slowly. Given the fact that such fall are quite slow, conventional inertial sensor often cannot capture such falls. So to address this challenge, a new wearable sensor was developed for detecting slow fall, and which is an integration of a wearable sensor and a wall mount reference sensor. So the wearable sensor is an integration of IMU with a barometric sensor, and the reference sensor is just a barometric sensor mounted on the wall at a location about 1 meter above ground. As an example, during a slow fall, the accelerometer and gyroscope of the IMU can capture the movements, the accelerations, and the barometric sensor can detect the change of elevations from sitting to falling down onto the ground. Hence, fall can clearly be seen from the differences between the barometric sensors on the body and the reference sensor mounted on the wall. Although the IMU sensor can detect the movements during the slow fall, the signal patterns could appear very similar to one tapping onto the sensor while lying down on the bed. Hence, using only an IMU sensor is not sufficient to provide accurate detection of slow fall. So we have to rely on a barometric sensor, which does not show much variations between the sensor on the wall and the sensor on the body. So to detect slow fall, we designed a deep learning architecture to fuse the IMU and the barometric sensor data. The deep learning framework is mainly a 1D convolutional networks combined with LSTM layers to extract the optimal features and capture the transitional properties of the sensor data to detect slow falls. To validate the proposed wearable sensor system, we have designed an experiment protocol, which is an extension from a fall detection protocol from previous studies to include slow fall episodes or events. So in total, 30 different types of events are defined, where half are related to activities of daily livings and half are related to falls. For each type of force, we collect 30 sets of data. with the aim of developing a subject-independent system, so which means the system can work on any subjects. The deep learning model was trained using only one subject data with about 600 events and tested on data from 10 subjects. The participants were asked to wear the sensor around the waist and simulate the 30 events described in the protocol. This graph shows the detection error rate of the 30 events. So it's quite clear that the proposed IMU barometric methods outperforms the use of only IMU or only barometric sensors in detecting activities and falls. We have also conducted a comparative analysis on the classification methods to compare the proposed methods, proposed deep learning methods with other conventional machine learning methods. So the results have shown that the proposed deep learning neural network methods outperforms conventional machine learning methods such as SVM, KNN, random forests, and so on in detecting slow falls. So I have talked about a couple of sensing technologies, mainly for monitoring patients, subjects. So in most cases, when we talk about wearable sensing system, we often refer to systems which can monitor the physiological parameters of the user or the related context information. Of course, as Professor Stefan Leonard has also mentioned about some wearable devices with actuators. And also there's also some wearable robotic systems to assist older adults or patients. But one of the earliest wearable technologies could be the hearing aid, which is an enabling technology assisting those people with hearing loss. So hearing loss affects about 11 million people in the UK. So hearing aid mostly focus on sound amplifications and signal to noise ratio improvements. Commercially available technologies and cochlear implants can only benefit about 50% of the hearing impaired population, as these devices only address damages have incurred in the outer and middle ear up to the sensory organs, i.e. the cochlea. Patients with damaged or nerve degeneration past the middle ear will not be benefits from hearing aid or cochlear implants. So let me just go into a bit more details on how we perceive sound first. So our outer ear collects and recreate the incoming audio signals. The middle ear responsible for amplifying the incoming sound, and the inner ear cochlea analyze the sound and converts that into electrical impulses. So for those patients who have nerve damages beyond the middle ear, conventional sound amplifications of the provided by the hearing aid or the nerve stimulations provided by cochlear implants will basically not work. So to address the need of those patients, we propose a haptic feedback-based wearable device for hearing impaired. So we hypothesize that users can learn to perceive sound from their mental sensory sense. Hence, we have developed a concept prototype to demonstrate the possibility of sensing sound using tactile feedback. So it's designed as a pair of devices to be worn on the back of the ear to enable the user to sense the tactile feedback and to determine the direction of the sound's origin. However, given the wide spectrum of sounds can be heard by humans, it's not feasible to generate such wide variety of tactile feedback patterns and expect the user to be able to recognize a speech from such complex patterns. But when we look at the language, actually words are built from vowels and consonants. The different vowels sounds differently because of the harmonics. And during a speech, we can generate different vowels and consonants by moving our mouth. Our speech is made up of phonemes, and phonemes sounds the same in different pitch. This is how we recognize the word from a speech. So to enable the user to understand a conversation from their using their tactile sensing, our wearable device is designed to recognize the phonemes and generate the tactile feedback patterns. So a phoneme is the smallest units of sound in speech. There are approximately 44 or 45 of phonemes in the English language. So in our wearable device, we designed the system to recognize those phonemes and generate unique tactile feedback signals or patterns to represent each phonemes. So this diagram shows the design of a wearable device. So we first analyze the speech signal by break down the speech into phonemes and perform Fourier transform to extract the Fourier features, collect the characteristics of different phonemes, and it then perform classifications of the phonemes using machine learning methods. And the recognized phonemes will then converge to tactile signals by assigning a vibration patterns to each phoneme and apply the vibration patterns behind the subject's ear. So a proof of concept, or to prove the concept, an initial prototype with 3 vibration motor was designed, and each motor represent each bit in a 3-bit coded pattern based on the letters. So the 8 possible combinations are then assigned to the character H, E, L, O, W, and R and D, plus nothing. To test the concept, we attach the vibration motor onto the back of the hand of a subject, and she can recognize the character accurately after a bit of practice. This small initial experiment demonstrates the possibility of perceiving sound from a tactile feedback. So we later extend this design to include 5 vibration motors on each ear, and with 5 motors, it's possible to generate up to 32 combinations, and we can use it to represent 26 letters in the English language. Given that we can only collect limited data, and there are already well-established speech recognition algorithms and packages available, instead of developing our own, we use the off-the-shelf speech recognition package from Python instead of building ourselves. And among different speech recognition engines, we found that the Google provide the best results, although it needs the internet connections, and we use the Google speech recognition engine for recognizing the words and then convert that into phonemes. So this diagram shows the system, it's a system diagram of our proposed wearable device. which involves the steps of signal filtering, Fourier transform, harmonics extraction, speech recognition, and generate the tactile feedback patterns. Initial results shown the functions of the system, and initial experiments have conducted to demonstrate the concept. We are still in the process of extending the work and also expanding the experiments to show the potential of the proposed wearable devices for assisting people with hearing impairments and allow them to feel the words and potentially have a conversation with others using the device. So this is quite initial work. So we haven't finished the user studies for those sensors I've shown you today. They're all developed in the last couple of years, where in most cases we're under lockdown, so they're quite early stage developments. So at last, I just want to highlight, of course, the EMBS WBSS technical committee, which welcomes all the people interested in wearable biomedical sensor and systems to join the technical committee. And also, as Stefan has also mentioned, we are running annual conference BSN conference together with BHI. And next year, we're aiming to have a in-person conference in Athens, but yet to be announced because there's still a lot of uncertainty given the current pandemic. So thank you very much.
Thank you very much, Benny, for the interesting talk, particularly the last research line was very novel and promising to my personal opinion. I would like to ask the audience for questions. Of course, we have some time. Okay, questions are arriving. Okay, I have a question from Valentina Casadei. Are you looking for developing a system that can detect the difference between COVID-19 symptoms and other lung diseases, for example, asthma attacks?
It is possible for COVID-19 and also other diseases. That sensor we developed when it was in the beginning of 2020. So at that time, COVID-19 was really serious. So we start off with COVID-19, looking at those symptoms. But of course, the sensor can be extended and used for other respiratory diseases.
Okay. Any other questions from the audience? Okay, yes, another question. Could you comment on current wearables for risk assessment in elderly population? Most of the work focuses on prospective students using inertial sensors.
Yeah, so there are a lot of commercial available like fall detection sensors and devices you can buy even from Amazon, I believe. But most of them doesn't really work well. And in terms of fall preventions, there's a number of groups developing different approach using sensors to detecting the precursors of fall. But the challenge of fall detection is we cannot induce fall on the elderly, which is the ethics committee. Again, they don't allow us to do that. But all in all, we can simulate a lot of data. Most of the work are done through simulations with actors, with like healthy subjects, and there are quite a lot of publications always showing the potentials of fall preventions, and some of them, well, at the moment, what we are trying to do is actually aiming for deployments. So probably like most of the research from conducting studies or doing a lab experiments to the user studies to clinical trial. Each step is a major challenge. They have different challenges. And then the next level is from after the clinical trial going into deployments to multiple sites to show the potential of the device. So not many groups have reached that stage yet. There's still a lot of potential. And as far as what I can see, there isn't a simple commercial solution as yet. So we still have to do more.
Yes, I agree. One of the major challenges with fault detection is the scarcity of real data. Although I have seen there are coming up a few open data sets with real data, but they are quite limited. So one of the challenges is definitely in this one. I have a quick question for you. In one of your slides, I read about fall prevention, which is quite, I am sure, challenges because, you know, literature is quite wide on fall detection systems.
Yeah.
A few works focus on fall prediction, but fall prevention looks very challenging. Can you comment on this?
Yes, it is. I mean, we have started work on that for quite a number of years, because there is probably Paolo is here. He knows very well. There is a Oxford score for fall to assess the risk of fall. So they're using basically something asked the elderly, in some of which asked the elderly to close the eye and turn around and see their balance. So there are already a standard kind of like metric where clinicians use to assess the risk of fall. And to be honest, sensors can do a better job because instead of using, watching the elderly, the sensor can give us more accurate data, and we can detect those. We can use, and from our previous study, we show that yes, we can quantify the risk of fall. So if the elderly have a higher risk of fall, then we can raise the alarm to be potentially prevent the fall. And because for those high risk elderly with high fall risk, they should admit to the hospital and probably some interventions in order to help them to build up the muscles and strength.
That's right. There is a hand raised from Marian Ravan. Can you, if you have a question, can you write it down on the Q&A tool or on the chat, please? I think there is time for just one quick question. Then I will pass the floor to Professor Bonato for his closing remarks. Okay, not sure. Maybe Mariana's raised the hand by mistake. Okay, that's fine. So let me thank again Benny for this very interesting talk, and I am very pleased to give the floor to Professor Bonato for the closing remarks of this very interesting first day of this WSAIM workshop. Please, Paolo.
Thank you very much, Raffaele. And my job is very simple. I have to thank these speakers. We got really fantastic lectures today. And I need to encourage you to attend, of course, another exciting program tomorrow. We're very pleased with all the lectures that were given today. We're very grateful to both the speakers that you see in the slide, as well as the members of the organizing committee that recruited them. We have a fantastic lineup of speakers for tomorrow. But before we start the main program, we have a really super cool, if I can call it that way, initiative by the IEEE Young Professional Group. We are very grateful to this group that organized this competition. As I trust many of you notice, we have this pitch competition for tomorrow, which will start at 9:30 a.m. Central European Time. So very early for those of us that are in North and South America, but perhaps worth getting up early to see at least the tail of it toward the very end, about 11:20 a.m. Central European Time. So there will be an award at the end. The winner will receive 500 euros, and we're looking forward very much to all the presentations by the members of this young professional group. We're then going to have a very exciting program starting around 11:30, and Professor Occhipinti will continue this track that we started today. And then we have two extremely exciting tracks tomorrow, one devoted to essentially the future of wearable technology, its commercialization, and a second one with primary focus on artificial intelligence, machine learning techniques for the analysis of wearable sensor data. So with that, let me close for today. We're very much looking forward to seeing you tomorrow. Thank you so much for attending today. And once again, looking forward to seeing you tomorrow. Carlo, if you want just to say a final goodbye on behalf of the organizing committee, go ahead.
Yeah, thank you, Professor. Yeah, I just want to say thank you, everybody, and see you tomorrow. It was a splendid day with a lot of amazing talks and inspiring presentation. We hope tomorrow to have the same level of speakers. And thank you to all the attendees for joining our numerous sessions. And that's all. Thank you, everybody. See you tomorrow.
Thank you, Carlo. Thank you, everybody. Bye-bye now.
Bye-bye.
Bye-bye, everybody.
Bye.
Bye.